Hello. Yeah, I can hear you. Hello.
कर दीजिए present. Also clear.
Yeah, thank you.
Just give me a minute, sir.
Yeah, sure.
So I welcome on behalf of Sardar Patel Institute of Technology and Walchand College of Engineering and C.I.T. all participants on the day 5 of HPC High Performance Computing and Artificial Intelligence NSM sponsored faculty development program hosted at Sardar Patel Institute of Technology. So today we have a guest expert speaker from IIT Goa, Dr. Sheetala Prasad. He is an assistant professor in Department of Computer Science and Engineering at IIT Goa with expertise in deep learning, pattern recognition, and computer drone vision. He holds a PhD from Indian Institute of Technology, Roorkee, and has previously worked as a scientist at the Institute for Infocom Research, I2R, under A-Star in Singapore. Research fellowship at Nanyang Technological University (NTU) in Singapore and CNRS in France. As a senior IEEE member, he has made notable contributions to the field and has received the Young Scientist and Next Skill Award in Artificial Intelligence. So, on behalf of CDAC, Walchand College of Engineering and Sardar Patel College of Engineering, we welcome you, sir, here. I request all participants please give a big round of applause to Dr. Sheetala Prasad.
Thank you very much. Thank you.
Over to you, sir.
Yeah, thank you very much for the introduction. So I'll share my screen.
Yes, sir.
Yeah. Let me know if it is visible.
Yes, sir. Your screen is visible.
Okay, fine. So I'll start with the introduction. So basically, I will be talking about HPC enabled edge computing for real-time communication systems as well as computer vision. So as an introduction already has been given, so I'll just quickly go through the overviews about my profile because it's necessary that you should be aware that whom you are listening to. So right now I'm assistant professor at IIT Goa. Prior to that, I was working as a scientist in A-Star Singapore, as already been mentioned. And prior to that, I was a postdoctoral fellowship and did my PhD from IIT Roorkee. Have several other achievements, and these are some of the publications and the conferences which we are hosting right now. So just a brief introduction about myself so that you can be aware of like whom you are listening to. So let's start with the artificial intelligence as the workshop or this FDP is basically focusing on HPC and artificial intelligence. So before we dive into the HPC and the need of exact HPC for artificial intelligence, let's try to figure out like why artificial intelligence really needs this kind of stuffs or equipments. So as a definition, very simple, majority of you might have already been aware of these things, so I'm just rebrushing them. So as we know that artificial intelligence is basically the kind of like engineering of making intelligent machines and programs. So that means like if we have someone if we have a if we have a kind of like situations where a doctor is going to give you a medicine for fever, and second time when you visit again he goes and asks for the medicine for fever, the doctor always gives him a paracetamol, say for example. So third time what will happen is like whenever patient will have a fever, he will instead of going to the doctor, he will just go and buy a paracetamol. So in that case, whether that particular patient is intelligent enough or he's just an expert because he knows that the pattern is something like that. So there comes like the question of making and engineering machines where artificial intelligence can come. So expert systems and artificial intelligence systems are a little bit different. In compared to that expert systems and at AI, we have some branch of machine learning, which is basically adding into the ability of learning things without being explicitly programmed. So now it can also question that this fever is because of malaria or because of some injury he got it, or stomach ache he has. So he will try to connect those informations and then try to come up with a prescription, something like that. Similarly, when we talk about deep learning is also a subset of machine learning, which is ultimately a subset of our AI. There we usually do learning based on our neural networks, and these neural networks are deep enough. That means multiple layers are being involved in this particular learning phase. So that's why we call it as a deep neural network. So this is, if it is clear, that this is how our scenarios will be going into. So from very standalone statistical AI methods, we are moving from machine learning to deep learning. That's why computation is keep on increasing day by day, day by day. So that's why what we can say is like artificial intelligence is now hand in hand with HPC, high performance computing. So before I dive into more details, let's try to figure out one small example so that it can give you a clear idea. On your screen, you are able to see some image, right? So I'm not sure whether I can have interactive sessions, but I'll just try to point out something. If anybody can answer, it will be good. On your screen, you can see some image, right? Uh, anything special you can see on the screen? So you can see that there is a waterfall, beautiful scenery is there, butterflies there, correct? There is a person who is walking in that surrounding, correct? Yeah, and that person is doing what? Listening to the music because he has headphone, but you cannot listen to the music, but still you can infer that this person is listening a music because he has an headphone, and that headphone is on their ear. So that means he's listening to the music. We can infer from that, correct? Even though we are not listening what music he is listening. Second thing is like, can you locate? If I ask you a question, that can you locate shoes in this particular image? Yes, and the color is white and blue, correct? And this is the shoe, right? So our brain is being designed or being trained in such a way that it can recognize any object in a 3D world. It has been trained from years after years. We are able to recognize this shoes as a shoes, and the audience or the participants present there, everybody will agree that this is a shoes. Nobody will be there who says that this is not a shoes, because every BNN, biological neural network, is being trained for this particular kind of 3D objects over years. So everybody can recognize this as a shoes. But this is not what our machine sees. This is what we as a human being sees objects in a three-dimensional world. So it's very easy for our brain to relate any object in three-dimensional rather than any other dimensionalities. But do you think like this is what we our computer also sees? So just to give an example, this is what our computer sees. So this is what our computer interprets an object. So there are several objects. Several objects will be represented with several other features. So every features will be responsible for some or the other things, and each feature is represented as one dimension. So compared to our real physical world, which we are used to it, our human brain, that is biological brain, is used to it. That is three-dimensional. But in a machine or a digital world, this dimensionality increases to even millions to billions. So, and this is what they actually have the features, or they actually learn things how it looks like or how it infer. So you might have, I think everybody might have used LLMs in their day-to-day life. I mean, I'm sure at least ChatGPT might have already been explored. Correct. So the dimensionality of that, or the number of parameters used in that particular model is millions, even billions. 7.5 billions or more than that also are being used to just to answer one single query from one single user. So that kind of dimensionality computation is there involved in this particular kind of things. So that's why HPC is the real leader. So what HPC is going to do is, or what this artificial intelligence is going to do is, they will come up with a kind of bridge between this three-dimensional world to n-dimensional world, that is your physical world to a digital world, so that they whatever we see, at least computer can infer from that, or whatever computer sees, we can infer something from that. So here is some one example you can see over here. Now at least some objects you can recognize on this particular, in this particular image, compared to the previous section, previous image. This image is much better, where you can at least refer to some objects based on my past BNN's knowledge. Correct. Say for example, if I just want to point out this particular thing, what do you think this will be?
Dog or wolf? A dog or a wolf?
Dog, dog or wolf? Correct. Any other answer?
Horse. Donkey.
Uh, Fox,
Fox.
horse. Okay, horse, puppy, dog, wolf. Any other answer? Monkey. Okay. So now the thing is like, why I'm asking this question is, when I asked where is the shoes, you everybody agreed with this thing,
Yes.
right? But when I asked that what is this creature, uh, multiple biological brain has multiple responses. Some says dog, some says fox, some says some other animals. Now the confusion starts building up. In the previous image here, nobody can identify what image it is, or what object it is, what creature it is. But when we try to reduce that n-dimensional to some pure dimension, say for example like this, our brain is trying to relate some of my knowledge, some of our knowledge, to identify this particular object. Correct. But still there is some confusion, because many of the informations are redundant, or many of the informations are not very clear to our biological brain. So that's why the response is a multiple response. It's getting confused. And if I say this is dog, and suddenly you say no, no, it's fox, might be possible that you can brainwash my neurons or weights, and then you can change it. Okay, yeah, yeah, it's a fox only, even though I was confirmed that this is a dog based on my knowledge. So that's what I wanted to point out over here. We as a human being mostly deal objects in three-dimensional, and we are comfortable with it. So we want to try to convert all our digital worlds towards, or at least close enough to our three-dimensional world in which we are familiar, so that we can identify what particular machine is learning, or what machine is going to give me as an answer. So this is one scenario, and now everything is clear till now: three-dimensional, n-dimensional, digital world, physical world, and the bridge between these two. This is what we are going to dive into in more details, a little bit with small mathematics, so that I can explain the complexities of these artificial intelligence or deep learning things, so that the real need of HPC will be into pictures. And then later I will show you some of the use cases or examples. So, if we talk about an image, for us, the image was like this. We can identify the shoes as a shoes over here. A man with a pink shirt, which is not very common, but yes, a man with a pink shirt is there. and everybody can identify that this shirt is a pink color shirt. This shirt has a t-shirt inside it, or white color, or something other details is much easier. For us, image is like this kind of structure, but for a computer, image is something like this, which is a numerical or a number matrix. I think majority of you might already been working on computer vision or image processing algorithms at least, so they might be very much familiar with these kind of things. So if a cat is being, if an image of a cat is being represented into a mathematical format, which is a matrix of different color channels. So say for example, this image is of 800 cross 600 with three color channels. That is your RGB. So this is basically what a computer sees, and an image can be represented as some kind of limit. Say for example, from 0 to 256 or 0 to 255. So the values of each and every matrix entities will be either from 0 to will be lying from 0 to 255, and that will complete the image, or that will completely represent as an image. So matrix is basically that. So this is what our problem definition is, and now we are going to solve. So you might have a idea, like when we have a matrix and we need to multiply that matrix with another matrix, it's a little bit more complicated. And suddenly when you have a matrix which is 800 cross 600 size, then if you multiply that 800 cross 600 with another 800 cross 600, that will be even more complications. So for that we need a HPC or high performance or GPU machines. So now let's take an example of image classifications. For example, an image is of 4 cross 4 sorry, 2 cross 2 pixels. That means total 4 pixels. So this cat can be represented as 56 to 231, 24, and 2. Correct. Now, what we need to identify is like whether these pixel belongs to which category, and the categories are three classes. That is dog, cat, and sheep. Correct. So, based on our biological neuron, we have replicated our ANN, that is our artificial neural networks. BNN say ANN, we have moved it. So we have copied the exact formula. Like we have some kind of information coming from the eyes to the retina. Retina will produce some kind of signals. That electric signal will be passed from neurons to neurons to neurons. Then there will be LOC. LOC is going to tell you what the person is, or what the human eyes is seeing. Same thing we have followed it over here also. So we have converted each and every image into a pixel format. Pixel will be represented with some kind of intensity values. That values will be having some kind of impulse, and that impulse is being passed through a neural network, which is having a kind of function which is going to sum all those informations together, and then multiply with some kind of weights will be used to identify whether that particular information is useful for me to classify some category or not. Because if you see this particular image, there might be uh, two or three key features because of which you identify that this might be a dog. Because first can be your nose, and then eyes, and there will be a kind of sharp shape. So because of this only, you might have made a conclusion that this might be a dog or a fox or any wolf or something. Correct. So you are identifying some kind of key features, and remaining others you are ignoring it, or you think like that is not that important. Correct. So that is what our weight is going to be used for. So it will be telling you that whether my 56 is useful, 231 is useful, 24 is useful, or 2 is useful. So that's what we are doing, a multiplication, and then we add some kind of bias to it, and then we get some kind of scores. The higher the scores, the better it belongs to that category, or has a higher probability to belong to that particular category. This is a rough scenario, and same we can do it for multiple images by learning this particular weights. So this particular W can be learned or can be used, updated repeatedly for several examples, and then we can come up with an optimal values. This is what we try to do it in our image classification deep learning things. And whenever we do this kind of approach, we have some kind of loss functions involved in it. Loss is why, because whenever we get some input, multiply with some weight, and then add a bias, and then get some kind of score, if that score is not correct, belonging to the correct class, in that case what we need to do is we need to again update my weight. And how to update and how much to update is basically been driven by this loss functions, which will tell you that okay, this particular image is wrongly classified but has a higher probability or is very close to the class. So that's why the weight should not be updated too drastically. And this is what been associated, or this is what been uh, told by this loss function. So based on the loss values, the weights will be updated by calculating the gradients in a back propagation manner. This is the clear scenario. If you want to see how this back propagation is basically happening, you can have this small piece of maths over here, and then you can see that how this loss has been there, and from iteration by iteration, how this loss is going to give you the value. So something like this over here. 3.2, 5.1 minus 1.7 was the score, and the loss was 2.9, and then the weight has been updated. And once the weight has been updated, the scores is 1.3, 4.9, 2.0. So that means car has the highest probability, so something like this. So this keeps on going iteration by iteration, and then we get some kind of optimal scores over here. Similarly, the same things can be represented like this also. You can see over here unnormalized probabilities is being defined over here, and also unnormalized log probabilities is bit defined. So both the things we have over here. So just to give you a notion of multinomial logistic regression. So this is what we are using as a deep learning image classification, using where we are using softmax for classifications. And this is another illustrations of how the weight is being learned. So step by step, this is one W weight vector with a loss of 1.25. Then that particular weight has been updated with these kind of additional information, that is 0.0001. And because of that addition, your loss has been changed from 1.255 to 2.5 to 1.25357. So this last three digit has been changed. So this is how actually they are trying to calculate the gradients, and then will update the weights step by step. And if you see the complete picture, this will look like this. So if you have a linear score function, this is f of wx. And if you have two layer neural network, then f will be defined as fw. That means second hidden layers weight, and maximum of 0 w1 x, where w1 is basically the first hidden layers weight. So x is your input, w1 is your hidden layers weights, and the h is the hidden layer. Second one is w2, then that's your second hidden layer weights, and then followed by s will be your scores for each and every 10 classes. And this is the pictorial diagram where you can see that this particular image belongs to a plane where I cannot see any plane, but these features are correlated to a plane class. So highest score will be given to a plane. So similarly, the others will be there. This is a truck, but even though we cannot see any truck, but this features are correlated to trucks. So that's why there is a big confusion that whatever computer sees, whether human also sees the same information. If not, then how to make sure that whatever machine learning or deep learning algorithms are giving me answer is correct or genuine. So this is what we try to do over here. A complete scenario will be given like this. So if you talk about deep learning things, deep learning thing is basically has a multiple layers of hidden layers. So this is how it works. You have an input image, you have convolution, you have ReLU, you have convolution, ReLU, then followed by the pooling layer. Similarly, again, this block has been repeated for several times, and at the end, what we have is we have a fully connected layer, which is going to tell me the highest score of that particular class. And this is how it works. So the class which is having the highest score, that particular image is correlated to that particular class. And if it is wrongly correlated, then there will be a back propagation, and then weights will be updated at several levels. And how these weights will be updated, there is some kind of learning rate involved that will actually control the weight updates parameters too. Next, this is another overview where you can see how this actually converts into a feature level information. So if you have an original input image and you want to classify it, this particular image belongs to which category, whether it is a class car category, class person category, or class animal category. then what we do is, or what a network does is, like, it will split the three channels and pass those informations to the first hidden layer, where the responsibility of the first hidden layer is to extract or to get a edge informations. Once the edge is being extracted, the original information is left over behind, and then those edges will try to connect with each other, and then they will try to form a kind of corner and contour informations. That is the responsibility of your second hidden layer. Second hidden layers will do all this kind of informations and then pass it to the third, fourth, and fifth hidden layer. And at the end, when we have some kind of object part informations, say for example in this case it is third hidden layer, the corresponding informations will be having some kind of weightage to each and every class, and then whichever class has the highest weightage, that particular input image will be related to that particular class. So here the person category will be highly mapped, because the training has been done in that way, right? So this is what we have in ANN, where we are using deep learning. In deep learning also we are using CNN based algorithms, but there are many other modules. But since this is not in CNN or deep learning workshop, so we'll talk about them as just an overview, so that you can have some flavor, but not too details to be dive into. So now, when we talk about the digital transformations or digital conversions from your physical world, or trying to see my physical world into a digital format, or by seeing digital seeing physical world using our digital devices to form a digital world, we have this kind of layout. We have edge devices, we have fog nodes, we have cloud devices or cloud nodes, which we called as a data centers. So there are thousands of data centers which has millions of fog nodes and which has billions of edge devices. So this is what our complete scenario will be, is which we want to resolve, or which we want to have a clear idea. So edge has a upper subset, fog, then there is a cloud, which is a data center. So majority of the task which we wanted to solve is like, we want our HPC being involved somewhere in our edge computing. So nowadays there are portable or mobile or very lightweighted HPC GPUs being designed for this kind of edge devices. So we wanted to use majority of computations over the edge, rather than passing everything to the server. And until and unless there is a real need, we do not pass those informations to data center, because in their communications will be coming into the pictures and might be some delays. So we'll talk about those things in more detail in the coming slides. So if we talk about the computations is basically divided into two sets over here, because in this scenario we have either a cloud based computing or we have an edge based computing. So cloud is basically when we have our devices, they are transmitting all the informations to the cloud and then getting a response from there and then acting on that. So that is what we have. So computation, so basically each and every bits of computations will be taken care by our cloud computing. So that will add some kind of delay over here. But in case of edge computing, all the informations will be computed over to that devices, until unless they really need some more detailed analysis. So that is what we wanted to show over here, that your computation takes place over here in edge computing, and in cloud computing, computation takes over here in the cloud. But doesn't mean that edge computing cannot have a cloud based computations. They do can have, but they will minimize as much as possible, right? So if we talk about the challenges of cloud based communication systems, there are three major challenges. There are many, but we'll talk about the three major challenges. First is your high latency data transmissions to and from the cloud, introduces a delay that can impact real time performance. So for example, if there is a car to be driven or automated car, and each and every instructions has to be passed to the server and then compute it there, get the information and come back and then act. So in that case, what will happen, this car has some speed, and because of that speed it might lead to a dangerous situations when your computation is being performing in cloud. So we wanted to make sure that the computation is there on the car itself, so that it can take a decision, make a move very quickly. Or or at least like a near real time performance. So that is how we see it. Right. So this is one first limitations. Second limitations is your limited bandwidth. So cloud computing centers can become overloaded with the data traffic, because nowadays we have too many devices. As I showed you the diagram, that there are billions of edge devices, and everybody, if it they tries to send it to the cloud or to the to the server data center, there might be a situation that the data traffic is too much, and because of that there will be a crash on data clouds. So you might have heard recent news when there was a Ghibli style creations by chat gpts and various other AI image generation platforms, image generation platforms. uh, there were uh, there were some reports where our data centers was actually melted because of this heavy data transfer requests. So that scenario was actually been found there. So if that is the case, this is a major limitations, where bandwidth will be limited, uh, a data center can handle only few tasks, but few tasks will be not, and it will be like overloaded many a times, and it can generate too much of heat, and then at the end it can result to malfunctioning of a data center, or it can lead to a fire or other disaster. So that is the second. Third one is your security concerns. So majority of many of the times these edge devices are personal devices, or they don't want to transfer the information to the public domain. But because of this computation cloud-based service, there might be a situation that sensitive communications data may be vulnerable to security breaching breach when the transmissions over the public transport public network is being done. So these are the three major things which we need to remember, like whenever we do a kind of like whether we have to go for edge computing or whether we have to go for a cloud computing based services. So these things are going to be in a major picture. But when we do edge computing, there are some plus and minus too. Processing data close to its source, that means every information will be there at the device itself, and they will try to do maximum computations which is possible. They will try to do it on the edge device. That will ultimately lead to a reductions in the latency, and also improves the responsiveness. uh, it will enable the real time decision making, but majority of the decisions of course can be made by the edge device itself. But if the computation requires a database or some kind of file handling or search from the internet, then in that case they have to transfer, or they have to be relied on the cloud based service. So in that case it enables a real time decision making, but has some limitations. Not every decisions can be made where there is a data set requirement or data dependencies is there. More efficient use of bandwidth. So this is also one of the best way of using our bandwidth, because we are not transmitting each and every bits and bytes to the server or to the data center. In that case it will be limiting, or it will be not damaging the or not overloading the data center, and data center will also work very efficiently. So majority of the tasks will be performed on the cloud itself, sorry, edge itself. So now it comes like how HPC and edge is being defined. So HPC for edge computing, high performance computing capabilities at the edge, is basically we are also going to have some kind of replicas of our cloud-based services, or we are going to enable some complex data processing tasks locally, and supports real-time analysis by using a light or tiny ML algorithms. Like we have some, other than your machine learning, deep learning, we also have one small subset which is called as a tiny ML. So these algorithms will be optimized for our edge devices, or will be optimized for our edge-based HPCs, where the computation power is a battery dependent source, so that the compression will be minimized, or will be having as less as possible, and that will improve the decision making accuracy. So basically we are clubbing the good things of HPC and also good thing of edge together to form HPC for cloud computing. So that's how we introduce this HPC for edge devices. Secondly, there might be a question like what are the benefits of this kind of edge based HPCs. So the benefits of HPC enabled edge computing for real time communication systems can be few. I'll just list it four. First is your ultra light latency communication. That means it will enable your real time interactions and critical decision making, because at the time of like autonomous car, it cannot rely on the cloud based service, because it has to act immediately, whether it has to apply a soft brake, or whether it has to apply a hard brake, or whether it has to go with the same speed, can increase the speed or not. That decision has to be taken by this car on the spot, uh, uh, in the board itself. It cannot depend upon the cloud services too much. Then enhance the reliability. Local processing reduces the dependencies on the cloud resources, and also network connectivity. So there might be possibility that there is a network failure, or in that case the response is not going to be sent back to the device. So, and in that case device might land up into a dangerous situation. So that's why these kind of services, edge based or edge enabled edge computing, sorry, HPC enabled edge computing will be a good solution, or will be a positive things for this. Thirdly, it also improves the security, because the data is not being transferred to the any server, or to the any web via any public thing. So basically, it will minimize the security risk, and also it will increase the scalability, because it will enable the flexibility dependencies to meet the diverse communication needs. So this will actually also helps in the scalability scenario too. So this is one thing I wanted to tell about the HPC enabled edge computing. Now let's try to see where HPC for the real time communication systems, like the challenge where it can come into the picture is your traditional cloud based processing can introduce a latency. That's why it can be a challenge. Limits to the power consumptions at the network edge can handle complex data analysis. Security concerns raised when processing sensitive data at the edge is some of the challenges of communications. So this is what uh, your HPC for real-time communication systems might face. Now, as a solution, HPC-enabled edge computing, we can merge the power of HPC with the distributed processing of edge computing. So we can have some kind of like federated learning concepts for edge devices. So where the computation which is not been possible by the local or the edge device itself, then it can pass it through the local edge, and then it can do a kind of like federated learning something like a federated learning concept can be involved there. So basically uh, uh, a car can take a help of another car to solve some kind of scenarios which is nearby to itself. So instead of going to the cloud and then doing that communications, we can have a car to car communications, or something like that. So basically your edge HPC, your edge will be communicated with each other to form a kind of like a local cluster of your HPCs. HPC systems can be HPC systems are miniaturized and deployed at the network edge. So that's what we call it as a network edge. Enables the real-time processing for the complex, which is again the same scenario which we have already dealt with. That is your source and latency. Latency reductions improves the decision making, yes, of course. So these is one of the solutions. So now let's try to dive into back to the deep learning, because we have already seen these many situations where our HPC enabled edge device is going to solve many purpose, but then how we are going to deploy all those algorithms there in there so that it can solve the purpose of our autonomous car, say for example. So whenever we have a deep learning situation, so since I am already talked about AI, ML, and DL, when we can use DL, so whenever there is a kind of like simpler models doesn't achieves high accuracy, then you can use of course a deep learning. You have complex patterns where your standalone machine learning algorithm doesn't work much better, then you can use DL. Where you have high dimensionality data, you can use DL. When you have where you have the dimension of times in a vector, are kind of like sequences, then you can use deep learning. Where you can traditionally stick to your machine learning, in that case when you should you should stick to traditional machine learning, have a high quality low dimensionality data, then machine learning can work much better. So similarly, the other requirements are also there. So what we are trying to do is, over here we are trying to find out the algorithms, right algorithms suitable for our edge devices, so that they can pretend to be a edge network, to form a kind of a local edge based HPC services. So we are trying to find out those kind of solutions where this deep learning can be directly implemented or optimized, or we can directly use our traditional machine learning, statistical machine learnings to be deployed onto the edge device, and then that can serve a service. So one of the examples I can give you, with some insights, is like, whenever we have autonomous driving or such kind of the situations, there might be a situations that uh, the objects which we are looking for, or the autonomous car is looking for or driving, while driving, there might be a situation that multiple objects, from multiple views, they can be misleading. Say for example, one of the example I can give you is, if you have a circle, if you have a sphere, and if you have a cylinder. So for these three objects, if you there is one view in which every three objects will look like a circle only. They will all belong to a circle category. So at that time, what will happen is, your three classes will be classified into one single class. So that is going to trouble in the decision making. So there is a situation where your multiple views of objects can be recognized as different objects, even though one of the view of category A is similar to category B one view. We have to make sure that these two categories are two different, even though their views at, say for example, v view, v1 view, are similar. So that's what we have a real challenge. There might be a situation that's, where we have a category of fan, but these fan categories, when we dive into this fan category, we can see that there are fans with a three bladed, there are fan with two bladed, there are fan with six bladed or even more, fans without any cover, fans with cover. So these are all in the category of fans. So we are trying to, there the real challenge is like, we have to come up with a with an algorithm where they can actually learn this kind of latent space difference, and then can correlate to the real object scenario. So that's how we are trying to do it over here. So for this particular solutions, we have done one simple approach. We have done one simple experiments, and this is what the experiment looks like. So suppose we have a data sets which has several views. Several views means like an object can be viewed from 360 degree in one axis, but another axis another 360 degrees, so and so. So there can be like n numbers of views of an object from in any dimension. Even if in three dimension, it will be like many views. So what we are trying to do over here is like, out of those views, we are dividing those views into some view data sets. Say for example, this d1 is having some fixed view, and then we are passing that fixed view to to train our deep learning model, which is again trained on a HPC machine, which is having like a DGX which we have over here. So we train it over there, and that is the first phase of training, which is going to be passed to create a kind of like feature vector, which is again represented into a feature space. That feature space is responsible to identify a class as a class, and then based on the loss functions, we are going to again update this particular weights of the uh, deep learning models. So this is how the scenario actually goes from d1 to x to phase 1 theta, and then f is basically, here what we are doing is we are using, instead of using one single loss functions, we are using multiple loss functions. This is basically inferred from our classroom based scenarios. So because in our classroom what we have is, we are teaching to 30 students, but not all 30 students are topper in our subject. But out of these 30 students, there are a few students who are top in one subject, but another few students are top in another few subjects, and so and so. So not one single student is not one single student is a master of all the subjects. So there will be multiple different subjects, which is uh, and will have multiple different toppers. So same concept has been introduced over here. So there might be different responsible heads which is responsible for, say for example, view 1. There will be another responsible head which is responsible for view 2, view 3, view 4, and several others. So if we club them all together to form one single end-to-end systems, there might be a situation that we at the end we are going to get all the answers as a correct. So whenever we pass circle as a circle, then the response will be only circle. But when we pass sphere as a circle, then there will be different views being analyzed, and then we'll say that okay, that particular input is not a circle, but basically it is a sphere or it's a cylinder. Only one view is common, but the other views are not so common. So that's how we try to do it over here in this particular methodology. And I'll show you one of the experimental results also. This is the experimental results on ModelNet 40, which is one of the CAD based data sets, where you can see that the training has been done, and while training you can see there are some kind of validations. So these are the validations you can see. uh, this is only for scene data set. That means when we train for 10 classes, we are testing it on 10 classes. So based on that analysis, for our test set results shows like this. So this blue one is the proposed one, and this gray triangle, the bottom one, is basically the baseline. So you can see that when we have a multi-loss functions concept or multi-loss concepts with efficient net b0, we get higher performance compared to the baseline, and which is a significant improvement by this only small addition. So that means your different responsible heads will be responsible for different views, and then in that case cumulatively at the end we are going to make a decision, and that will lead to almost like 5 to 6% of boost. So this is what we have done it for the seen. Similarly, we have also done it for the unseen data sets, where your unseen data set is also having a better response with a clear difference of more than 5 to 6% improvement. You can see over here the lowest graph, which is in gray triangular, is the baseline, and the above blue graph is the proposed method, where they are using a multi-loss functions with different models. So the best model which we are showing over here for unseen one is your ResNet 18 multimode. So this is how it we proved that this particular concepts actually worked, and HPC actually solved this problem very efficiently by using or incorporating algorithms in a parallel scenario. So this is for unseen ones. Similarly, we have performed for another data sets, which is uh, MCB, that is your mechanical component data sets, and there also we have seen similar patterns. So here you can see the graph how it grows, and while it is growing, you can see that your baseline is getting saturated. Your baseline is getting saturated, and because of that, it cannot perform more than that. So, for example, if your baseline is giving you 81% accuracy, it will stop there 81% only and will not go beyond that. But the yellow one, you can see it started from very low, but while going step by step, at the end it reaches to a maximum goal, which is compared to your blue one. You can see that it stopped over here, but your yellow one reached on the top. So that means the same data set, same model, but slightly different learning approach gives you a better accuracy, and there is no saturations. And similarly, we also try to compute the parameter involved in this particular uh, approach. We can see that whenever we use these different types of models. So if you are not aware, I'll just let you know that these are different deep learning models which is responsible for image classifications, or any other task also you can use it, but here we are using for image classification. So here you can see that VGG is having 15.5 flops. Similarly, your efficient net has efficient net B0 has 0.29 flops, and so on. So different models will have different sets of flops and different sets of parameters. But when we see compared with our model parameter as well as model flops, you can see that accuracy of efficient at B0 is having the highest compared to the original baseline. Baseline was having 64, and now it is having 72, which is like roughly 8% of improvement, uh, even though the number of flops is way lesser than the baseline. So that's one of the things which we have shown over here. Similarly, we showed experiments, or we did some furthermore experiments for different backbones and different approaches also. We saw that for seen as well as for unseen, in both the scenarios, the proposed improved versions of with a backbone is actually work sorry, not with the backbone, with the multi-loss, is actually performing way better than the actual baseline method, which is 71.2 and 64.4. So this is what we have done over here. Similarly, we did it for different views. So now we have introduced 12 views, you can see over here. So for this 12 views, this improved multi-loss is again performing better. So your baseline is 60.6, 60.2 for seen and unseen respectively, but your improved multi-loss is going to give you 65.4 and 65.7, which is much better than your baseline, like for example 5% improvement by just simple approach, that is your multi-loss approach, and learning in a view based fashion. So this is all possible because of our parallel structures. We have designed it in our DGX. So as a conclusion in this work is that multi-view for unseen objects recognition, a complex architectures is the best choice. So if you want to recognize an object, we need to use a complicated or complex network architectures, because multiple views can be correlated in that case easily. Your single standalone or vanilla architecture might not be that efficient. It can be easily uh, changed, or can be easily affected, or can be easily dealt with the noise. So next is your classroom based multi-loss training strategies converges the network much faster and with a higher rate also, like 6 to 8% higher than the baseline. And also the proposed learning progressive learning can be generic. It can be adopted to any kind of category, so not only for image classification, but it can also be adopted for the uh, uh, object detections scenario. So for that, we have also tried one more approach where we have done it in a way much parallel situation. So we have parallelized all the algorithms like this. So different views will be learned by different GPU nodes, and then club them all together to form one single max pooling, and then later we'd identify them based on the heat maps we have obtained. So if we use that kind of scenario, of course the computation will be distributed to multiple nodes, and it will be much faster, and we can land up into a much better representations of that particular object from the multiple views. And at the time of query, we can get that okay, this particular square net can be viewed from multiple views, and they can look like all these possible combinations. But at very last, like okay, out of top 10, maybe only last two will be the best classification, but other than that, everything is a match only. So this is what it will add into the confidence of that particular algorithm, that okay, whenever we have a query, it will visualize from multiple views and then will give you the answer not only based on one single view. So this is one examples we this is one of the work which we have done it recently. And now since we are talking about the multiple views, there might be a situation we can always ask, like okay, when we talk about multiple views, there might be a situation that okay, this view can be confused with the other views. So of course, in real world also, human brains get confused. Say for example, this is one of the image. What you can see in the image is there's a dog doing something, trying to see some object maybe on the terrace, right? Am I audible? Hello? Yeah. So on the screen you can see a dog seeing on peeping on the terrace, right? Do you think what it can do, or what it's trying to do? Anyone wants to answer? Okay. Dog is trying to climb on the tree. Sorry, ceiling, right? Sorry, terrace. Okay. So that is one of the intuitions. So now, if I say that whatever you are saying is just your perception, because based on your prior knowledge, you are using those knowledge to get a solution of this particular image for this particular image, correct? And if I say that whatever you had a prior knowledge is not going to be used over here because our brain is getting confused. Why? Because there is two eyes and a nose, which is very close to a dog's face, correct? But actually, when we see another view of this particular object, you will be very much surprised that this is not a dog, this is a cat. So the face was his body, his tail, basically, which was resembling like a dog. But when we see the complete picture, the other view of that object, then you realize that okay, that was just a kind of like misconfusion or with some misclassifications. But actually, your BNN was being uh, too much biased to your dog, because in general we see dog more common compared to the cats. Correct? Agree? So that's why our brain is highly biased towards the dog. Whenever we see this kind of information, immediately the first effect will be that okay, this is a dog, or this can be a dog with a higher confidence. But to recognize the first image as a cat image, I think rarely anybody will be agreeing that this is a cat. But when we see the second image, yes, everybody changes his mind, changes his brain weights to from a dog to a cat, right? Correct. So using this concepts over here, we move to the other examples where we had a task of identifying a text in a real scenario. Text means text like uh, joint, pain, something like this. So this is one text. Joint is one text instance. Pain is one text instance. So our task was to design an algorithm where it can detect these kind of text instances and then do some kind of inference or do some kind of actions on that. And the very sad point of this particular algorithms, deep learning or AI, is that they depend upon the data which we have to feed them. So what we did is like we tried to we tried to do a crowdsource based labeling and ask the labelers to label these data sets for us. And we had three labelers, labeler one, two, and three. So what happened is the labeler one understand my problem very well, and he has labeled word by word very well. But labeler 2 is little bit lazy. He understand my word very correctly, problem definition very correctly. He labeled these words very correctly, these instances very correctly, but he missed these small instances and also critical. So in that case, these informations when we pass it to the network, they will be treated as a wrong prediction. So that means for the first image, network has learned that this is one of the word instance, but from the second image, the network is getting rolled back that this is not a word because there is no annotations over here. And similarly, from the third image, you can see third labeler is even more lazier, and he did what? He created one single word. So for him, when you pass the this particular image to the network will say, uh, private is not a word instance. Private car park Leon walks church is one single word text instance, which is completely wrong. So these two images will be acting as a noise to my first image, and in that case, what will happen is my data or AI based algorithm will not reach to a maximum accuracy. It will be confused, or it will be toggling between at some percentage, say for example 50% or 60%, it cannot go across that percentage because you have added noise. So that's what we are wanted to tell you, that here AI is totally a data dependent algorithm, data centric algorithm. So if we pass a correct data to the algorithm will give you a higher accuracy, otherwise it will mislead you. So that's what we wanted to tell you. So make a label why consistence, and let's try to see that based on that we have done one small experiment which was titled as object informations for a text spotting in a natural scenario. So this is one of the examples you can see. Easy to get confused is the quotation, where you can see some image over here. if you don't use your prior knowledge, what you can see on the screen is yeah, elephant, because your knowledge is already been trained on elephant or animals. But suppose if your brain is only trained on characters or text recognition, then what text or what character you are seeing over here? J, correct. So if our brain is only trained on the alphabets, character, or text instances, then it's high chances that we will be seeing this image as a J. But if we use our prior knowledge that okay, uh, this kind of texture information is a elephant's trunk information, then in that case we can realize that okay, this is a false alarm. This is not J. This can be a elephant's trunk. But if our algorithm is only trained on text information, then it will give you a text that this is a J with a 50% confidence. Similarly, when we see this image, this is also one of the image where your algorithm gets confused. This image is closely mapped to what character? Can you? This image is 92% confident that this is a text, but what text character? M. This is a kind of like M. If you reverse it upside down, then it is a W. And also, if we crop them all, it might be a closely matched to a V. So that's why the network is 92% confident that this is a character letter. Similarly, in this case, you can see that this can be I, L, this can be 1. So this is also 84% confident that this is a character. But if you see the complete picture, none of them are characters. So the question comes is like why this network is getting confused. Network is getting confused why? Because he doesn't know anything about other than the text. So if you know only about the text, then you will be too much biased, and you will try to find text everywhere in the image. That is what our machine also does. So it will keep on trying to find text informations everywhere, no matter whether that is actually a text or a not, or a fake text. So for that, what we need to do is we need to also understand the background information, back information. So that means before we analyze that whether it is a text, we should know that if it is a text, then where it is lying behind. So for that, what we did is we did a small experiment that before we dive into the text analysis, let's try to analyze or understand the object informations. So there are some objects over here, car, and if we want to have a car, if we want to have a text, then there should be a car. There should be a car. Then there should be a car plate. Then if there is a car plate, there will be a text informations. Correct. And in that scenario, my false alarm will be minimized. Understand? So if I have a signboard, there might be possibility that that signboard has some kind of text informations or text instances. So the first and the most important task is to identify a positive reason and a negative reason where text can be or where text cannot be. So if we know about those informations, then it is way much easier for a network model to understand or to design this kind of scenarios in a way well mannered. So we designed a parallel scenario for this situations where we understand the image object first before we dive into the text analysis. So parallelly, we have done this kind of approach, and then we use the first information, that is our object information, as an attention mechanism to our text information. So here you can see the dark one is basically your object detector without any class label. So we have removed this class label from this particular image, and then we pass it to the text detector. So the same image will be analyzed for positive and negative reason by the first block, and the second block is going to find out the text instance. And if that text instance is on the positive reason, then that is a correct text instance to be detected. If it is on the negative, let's say for example, if it has detected something on the grass, then it's a negative or it's a false positive alarm. And this is the small concept which we have chosen and which we have inherited into our algorithm, and then based on that we have tried with some random images, and there it's working way much better. compared to the previous past informations models. And now network is not getting confused. So one example I can show you that this particular scenario which I have just now narrated is actually working or not. Let's try to figure out on this particular text instances, right? The confidence level of this particular text instance is what? 95.8, correct? So now what we are going to do is we are going to introduce a positive and a negative reason close to this particular text instance. And then we see the confidence rate of that particular text instance. So if we introduce a car is a positive text instance. That means because car is a positive because we have a car plate and the car plate can have a the car plate number. So that's a positive instance. So when we introduce a positive instance close to that text instance, the confidence rate increases from 95 to 94, 97% accuracy. Correct. But if I introduce a positive instance which is not very close to this text instance, say for example this one, then there is no effect. There's no effect over here. Similarly, if I introduce a negative instance, the confidence rate starts decreasing. So from 97.4 to 97.2, it is downfall. And if I introduce this negative sample close enough, because an elephant is a natural, an elephant is a god-made creature and not a human-made or man-made, and text can only occur on man-made things, right? Mostly. So if I introduce this negative close to the text instance, then the confidence rate suddenly falls down from 97 to 86.9. This is what it will confirm that, okay, this particular algorithm is working way much better because my prior knowledge is really a good, is important to identify something based on that. And this is what we human being also does it in a day-to-day life. Whenever we make a decision, we make the decision based on our prior knowledge, not based on the current situation only, right? So, in this race of this identification and classifications, we have now landed into an era of drone things. So now everybody is very much interested in drones, and for each and every task, we are trying to introduce drones. So the drone was being first used, or drone is basically called as an unmanned vehicle. So this unmanned vehicle was first being, targeted in 1849, where Austria dropped 200 bombs on Venus, but because of the miscalculation of the wind direction, that bomb fall on themselves only. So from there, we started working on the unmanned vehicles, which can be used for doing this kind of activities or even better activities, dropping some food services and all. So for that, we are doing some kind of drone boot camps in IIT Goa. Every 2 months or 3 months we are teaching them how to design the drones, or how to program it, how to design the edge algorithms for our drones things, and how drone to drone communications will take place. So this is a project being funded by MITI, that is government of India. So if you are interested, you can also join it. I think next boot camp we'll be having in May or end of June. We'll be posting it soon. So this is one of the things which we are doing it recently. Now let's dive into the drone things, because drone is also nowadays part of edge based HPCs. So if we talk about drone, what are the components we have in drone and how they can be served as a HPC? So we have motors, we have frames, we have propellers, we have speed controllers, and we have flight controllers. These flight controllers can be treated as a kind of like small computing unit for our uh, AI algorithms. So we have, along with this flight controllers, we have also deployed some Raspberry Pis, some other edge devices also, like NVIDIA Jetson, and we are using that kind of devices to solve our machine learning algorithms or deep learning algorithms to control the drone, or do a signal to flight control, give a signal to the flight controller, and flight controller will distribute the power to other parts, other components, and then do that operation. And in that case, as a payload, because we are working mostly on the computer vision side, so as a payload, we are adding a camera to this. But this camera can also be of multiple types, like your visual stereo, your laser based, or your monocular cameras. And because of these types of cameras, we can solve several purposes. Say, for example, if you have a task to identify or detect some objects, then you can use optical cameras. If you have a task to identify someone in the night vision, then you can use something like IR cameras or some fire rescue things. You can use IR cameras. If you have a thermal, say for example, situations where there was a low latency, then you can use thermal cameras also. If you have uh, applications where agriculture has been involved, then you can use multispectrum cameras to identify different types of crops or different types of yields, fruits. If you have construction based things, then you can use, of course, or obstacle detection based or reconstruction based, then you can use lidar cameras as a payload to the drone. But these all different types of cameras will have some kind of limitations or challenges, that their resolution is one of the biggest challenge. The field of view is challenge. Your weight, if you add too heavy things, then the drone might not take up. If that is the situation, then your cost will also increase. But if you have a big amount of money, then you can go for any kind of cameras or any kind of drones which can work for you. But if you don't have much, or if you have a limited budget, then these parameters has to come into the picture while designing or while coming up with your own algorithms. So based on those things, if I try to categorize the types of unmanned vehicles used in our day-to-day life or in applications, there can be a drone which can be used for our construction sites to measure the safety. There can be a drone which can be used in agriculture to spray the fertilizers or pesticides. There can be a drone to monitor or do the action recognitions. There can be a drone to do fire controls. There can be drones which can be designed for some kind of monitoring. There can be drones which can be designed only for 3D constructions, where they can construct sites, or they can work where there is a dangerous sites. There can be drones which can deliver. There can be drones which can also detect the safety of the instruments and the vehicles in the construction sites design. There can be drones to control the traffic police, traffic. There can be drones which can be used for law and order monitoring. They can have speakers, lasers, and other accessories to control the uh, crowd. They can be drones which can monitor the water surface, drones to do a city scan, that is 3D city map, and also drones can be used for diving inside the water to do a water survey. Researchers are also working on nano drones, which is one of the research from Harvard University, that can actually dive inside your blood vessels and do some kind of operations and dissolve there. So here the drone difference is, like, they are not motor based drones; they are the protein based drones. So they are going to do this kind of operations there. So based on these concepts, we have also designed some of the drones at our place. So these are the drones which we have designed, and if you see that these IIT drones are working way much better, and they have some you can see that how they looks like. These are the drones which we call it as a drone eye, which is used for small operations like navigation operations. They have some swarm intelligence design in that, uh, and they can communicate between one drone to other drone. That's part I will also show you. So here you can see, instead of lifting up skating because of the air pressure, AC was on, then we have taken it outside, and then it's working way much better. It's took off. Barometer has been added over there to measure the air pressure and then calibrate it and then do the operations. So these are the drones which was only 2000 2500. You can also design it. We have the videos and the list of components used in that particular drone. Then we have designed the mission planner, different versions of drones with a GPU, which can be more stable. This is a mission planner because we can plan our missions way before we fly it out. Because flying a drone is a big challenge, because everybody has to focus. I mean, the person or the pilot has to focus on the drone where it is and then control it. But this mission planner is a way simpler thing. You just need to press the button, and the drone will take off and then do the service and then come back to the home positions. And what those services are, we have already planned it beforehand. So these are different components, we different drones we have designed in our lab. This is what we are trying to do it, drone to drone communication at IRC. One drone is there, and this drone is trying to communicate with other drone flight controller over here, you can see. And then based on that, they are passing some information. So something like that, we are trying to work out so that these drones can be used for our edge based HPC or edge based networking can be created, and then they can do some kind of services to us. And along with that, we are also trying to work out with another types of communications where multiple drones can be controlled by using some kind of command. So there's kind of yeah, one drone is working, giving a signal to the other drone, and the other drone is giving a signal to the other drone. So somehow something like that, we are going to do it, and drone is working way much better. Both the drones are working. Similarly, we have done some few more experiments on this, and yes, we introduced some kind of like broadcasting based communication so that it can communicate way much comfortably easier for us. But here the problem is like when we add a payload, the same command for the first drone is lifting it more higher compared to the second drone, because second drone has a camera as a payload. Because of that, the battery is discharging in different fashion, and that because of that, this drone is not taking that much up, even though the command is same for both the drones. So we are working in that sense, how we can make it more optimized. But along with this drone, when we have a drone as a vision thing, there is one of the biggest challenge, which is your resolution. So if I ask you as a participants, what you are seeing on the screen, can you see anything on your screen? What is that? Can you assume?
Not visible.
Not visible. That means information is very less for you.
Yes.
Might be possible that the drone is at 30-meter height. But what if now, if I make it more closer?
It's a kitten.
It's a kitten. Okay. Any other answer?
Maybe a pup.
Maybe a
Pup. Black.
puppy.
Okay.
Okay.
Black pup.
So everybody agrees with this, a kitten or a puppy.
Black
So
pup.
here the concept says is like whenever we have more informations, our clarity of making a decision is more clearer or more higher. The confidence rate is more higher. In the first case, you were like almost clueless what is this object, but in the second case, at least you have come up with two categories, two class categories, which was on which your brain was already been trained. But if I add more details, now you are more clear. Is it still kitten?
No.
No. Some new character has came into the picture, right? Yes. So this is what I also wanted to point over here. Resolution is way much important. So flying a drone from 10 meter to 20 meter to 30 meter has different levels of details. So these levels of details can be optimized, can be regenerated, or can be used or can we have a algorithm where minimum features can be used to recognize some objects, or is it difficult for us? That is what we are trying to do it. But even though if you recognize an object as an object with 100% accuracy, or maybe the class is very 100% correct, there might be a situation where you have landed up to a condition that whether this particular character is real or fake. Is it real or fake?
Egg.
Fake. uh, but next my question was, if you say any answer with whether it is real or fake, you have to justify it. Can you quantify that? If it is fake, then because of what?
So the background, surrounding background, is sitting on something like cloth.
So you said like background and foreground is not matching
Yeah.
basically, and because of that you say conclude that this is a fake thing.
So in the real life, these kind of
Okay, so all these informations are coming because you have a prior knowledge. But what if my model is only trained to identify this object? Will it be able to identify whether it is real or fake? No, right?
No. No.
So this is why we are trying to come up with another approach where we are going to identify a person based on their multiple views. Say, for example, this guy is recognized as, say, person one. This is person two from the backside. But is it possible for me to recognize these two guys as person one and person two?
Yes.
This is person two or this is person two?
Behind.
The blue one is person two or person one?
Person one.
person one.
Person one. Why? You did not see his face in the first go, but still you are able to recognize this one as a person one, because you are not only focusing on the facial appearance, but also you are focusing on the other informations. So to recognize an object is or to recognize a person is we don't have to really depend upon the face informations, correct? Not only depend upon the face information, we can also depend upon the other features. So that is what we are trying to do it. We are parallelly learning all these features together to come and form one single feature vector to relate that this is person one. Similarly for this case also. And there are several other views which can occur from different angles, right? And everything has to club together to one single vector or one single category. So this is a real challenge when we design these algorithms. So along with that, seeing all these situations, we have come up with an algorithm which can be used for our real scenario, something like this. Here you can see animation. What is this animation for? It's a kind of like junctions where multiple vehicles are coming here and there, and then there are majority of them are two wheelers, correct? So we have this is as a we have taken this as a problem definition, and this is our motivation also. And because of that, we have come up with a solution that can it be possible to design a drone algorithm or edge-based drone algorithms or edge-based HPC and drone-based algorithms where police can have these services to fly a drone and then monitor the traffic, and then also identify those people who are wearing helmets and who are not wearing helmets, and their license can be challaned. And this is what we call it as a sky guard. And this is one of the scenario where you can see that the drone has been deploying some algorithm. DJI is fixed on some location, some altitude, and then it's moving his head and then visualizing and recognizing different objects, whether that object is of their interest or not, trying to scan something, right? So this is if you are if you have been to IIT Goa, then it's you might have recognized it, but if you are not, then this is IIT Goa's boys hostel and girls hostel. And the problem definition is not that simple, because there might be a situation where we have a person with a turban. There might be a person multiple multiple person sitting on the bike. So which who is driver and who is co-passenger, we have to identify them. And there might be a situation where there's a person who is not driving a bike, but is in a line to a bike, so that algorithm so in that case algorithm might get confused that whether this person is a biker or this person is a biker. So that kind of challenge will always be there. There can be a challenge of this kind of seals in front of the bikes. There can be a situation where the bike is too fast and blurry motion is being recorded, and how we can identify that whether this is with and without helmet. Similarly, we can have multiple vehicles one after the other, and then difficult for algorithms to identify whether that is a bike or that is two wheeler or other any other vehicles. So these are the challenges which we have tackled in our algorithm, and we have trained it. And this is one of the small demo where our hostel students are trying to play with this drone and trying to identify whether this drone is actually working or not. So there might be some false alarms you might have you can see that it's trying to identify this particular security as no helmet, because for him it looks like that grill is basically a kind of like maybe bikes pattern. So in that case, it is giving a misclassification over there. But majority of the time, it's identifying correctly. So here the students are not being detected, but only those students which is on the bike, this they are detected. So this is what the demo of SkyGuard is. You could see. So better to wear helmet and drive your bikes. Right. So now let's try to move into the last section, which is computer vision in our real scenario. In our real scenario, computer visions can be deployed into various applications, and because of that complexity, high performance computing is the real need. And since performance computing has a band limitation, not every information can be passed to there. Edge-based high performance computing has to be incorporated, and that's what we have designed over here. And here, we saw that this edge based or HPC enabled edge computing is or can be used in autonomous vehicles, can be used in industrial applications, automations, can be used in smart cities, and also can be used in remote surgeries. And one of the biggest applications we can see is over here, smart city parking. So where your different sensors, so many sensors will be involved, sensor 1 to sensor n, then there will be a data collector, and then pre-processing computer vision algorithms will be involved, payment systems will be involved, applications for different mobile based, embedded based, edge device based applications will be involved. So you can see the complexity of simple smart city parking. Smart city parking has so many complications, which needs a real HPC enabled edge computing to be deployed. And that's what we have done it over here. This is one of our book which you can refer to, smart city parking, where we have landed up with several scenarios for vehicle detection, parking space detection, license plate detection, violation detections, traffic flow optimization, security and surveillance, maintaining and monitoring things can be done. All things can be done by deep learning algorithms. And since I told that deep learning is a very complicated algorithm and has lots of parameters, then how it can be deployed onto the edge devices, that is the next challenge which we need to deal with. These are some of the images taken from our smart city books. And this is one of the examples where your edge device is being used to identify cars and see whether that car is being correctly localized or not, or vehicles has been correctly localized, and with what kind of confidence, whether there is any safety issues or not. So this is what we are trying to see over here. The drone is detecting all those objects, and wherever it finds any fault, it might give you a red color box. So here you can see the red color box are there, some places for where it's things like there's some error. So drone is being used for monitoring things. Similarly, drones can be used for various other tasks also, something like this here. So we are using drones to monitor mask based facial recognitions. This is one of the applications where we are using edge based sorry, HPC enabled edge computing. Not exactly drone, but yeah, drone can also be used for mask based detections. So, to make it really possible, we have to come up with an algorithm where this trained algorithms, trained deep learning model algorithms can actually be deployed onto our edge devices. So, for that, we have some steps. So, when we have a real time machine learning algorithm, we have to convert that machine learning algorithms into or convert it into or quantize into a machine learn edge device based dependence. So we use that platform like TensorFlow Lite, we use TensorRT, we use ONX to quantize that model. And once it is quantized, we try to deploy it onto our edge devices, something like NVIDIA, Raspberry Pi, and many other. And then we try to really deploy it into our real scenario, bridge it in say for example in our marketplace or in uh, surveying phase, and then we collect the data or we do some kind of operation based on that. So this is what our vision in the real time scenario looks like when we have some of it. So these are the low power CPUs or high power CPUs, HPC based, or we can call it as an edge based devices, micro edge and mini edge, medium edge and heavy edge and cloud edge. So this is how we try to move from low to high end powered CPUs or GPUs. So this is another example which where we are using Raspberry Pi to do some kind of operations for road safety. So an algorithm has been designed to monitor whether this particular vehicle is having a good distance, safe distance from this in front vehicle or not. If it is not, then it will apply a soft brake. If it is with a good distance, then it will maintain the speed. So on the top, you can see that there is a red message, red color message, not safe. And when there is a safe, then it will say that it's in green, that it's a safe distance. So this is how it works over here. In this another image also, you can see that prediction is there's no car in front of it, so it is safe. Immediately when the car comes closer to the other car, this green message converts into a red message, and it will alarm that the distance between the front car and your car is not safe, so you apply a soft brake over here. So this is what we have done it as a part of our HPC enabled edge computing. And for that, what we need to do is we need to have a hardware based, HPC node based, and the software algorithm. These are the list of the algorithm. These are the list of the hardwares and the nodes which we are including in our computations. And there will be a big question like which and how we can decide which devices or which hardwares we should use for our computation. So these are some of the lists which you can see. Best GPU overall by a small margin. So if you want to do, which is like a Titan XP, which was way older, like almost 10 years back, absolute. Now we are having 5070, 5080. So we can work with that kind of devices. But these are some of the facts on which basis you can decide whether your this hardware is suitable for your task or not. Uh, the money is also, of course, a major factor. Whether you are a researcher or you want to actually deploy it into the edge space, so you can use different types of GPUs, TPUs, and there is also one thing which is NPUs. Nowadays, been designed for edge devices. These NPUs are basically neural processing units, which can also be used not only used for inference but also can be used for training purpose also. So one of the example is your Symbian's processor, which is a NPU based processor. So you can directly deploy your algorithms, deep learning algorithms onto that these kind of processors, and you can train it also. Not only inference, but you can also train it. You can use your large language model. You can use your VLMs. You can use any kind of things to train it onto that particular device processor and directly deploy it for the real field. And last slide is something where you can see the bridge from your edge to cloud and cloud to edge. So if everything is being computed onto your device itself, we are more closer towards edge computing. But if everything is computed onto the cloud, then we are more close to your cloud computing things. So this is one of the scenario where you can see or you can have a clear picture of edge and cloud. So that is all I have for today. So now I'm open for questions. If you have any questions related to any of my work or any kind of concepts, I'm open to answer for that. Participants, you have any questions related to these things, you can ask me.
How can the edge computing be used for AR and VR applications?
Sorry, edge computing can be used for.
AR and that is augmented reality and virtual reality.
Okay, okay, okay. So this edge computing nowadays, say for example, you have Google glasses and all, right? So they have a capability to process some kind of task. So this Google Glass is one of the example for you to see that this is really possible. And these Google glasses are also communicating with other servers also. So if the informations cannot be processed there or some information has to be fetched out, so they can connect with the servers and then get the information. So definitely HPC edge based computing can be used for AR and VR, where ultimately your edge is part of your cloud based services. So this figure uh, can be a clear idea to that. So whatever task, small tasks, say for example, identifying an object, that can be done on your edge device itself. But to render something or regenerate the different views of that particular object or the third dimensions of that particular object, maybe in that case, cloud has been cloud can be the best to compute there. So cloud service can be called in. So that's how edge enabled edge computing can be used for in AR and VR. So we definitely there are some devices which is already using all these things.
Shitla sir, one question related from the parallel computing.
Yes.
So I want to add the increase the accuracy of the deep learning. Okay,
Okay.
you
Okay.
give example there is a bus, then there is a different. So accuracy depend on the background. So can you give us some model like some background model is one node, some text related, human related from one node, and then we have to combine all data with suppose like the MPI, that is the message
Uh-huh.
processing,
Correct. Correct. Correct.
and we have to increase the accuracy.
Right.
Since we are in sequential, when we have to get, we have to do the some real time data like some TCN network. We have to do the real time
Correct.
content CNN. It's
Correct.
good, but when we get the accuracy depend on the background or some other related like the text related, it
Mm-hmm.
mostly background. So can we give the some specialized model from the different network, and then we have to combine all this network. We have to increase the accuracy, like what is our objective optimization of.
Correct. Correct.
So can we increase this within the parallel approach?
Yes, yes. I think that is definitely possible because when we have multiple models and uh, multiple models gives you multiple responses, you can definitely use parallel computing to do this multiple operations and come up with their own responses, and then at the end we can club them all together to form one single feature vector. As I showed you in the previous example also, where we had object informations in one thread, and we have text information in the other thread. So the based on the fusions, based on the message passing MPI, we club them all together to form that, okay, this is positive results for this text instance, and then the final answer will be depending upon the positive results only and not from the negative results. So both the threads or both the layers were working independently, and then later they are going to come up a decision that, okay, these are the correct things or not. So definitely to improve the performance, we can definitely use this kind of approach, but there are some limitations that where the informations cannot be shared, or they need to be processed on one single thread. So in that case, yes, of course, there might be a limitation that the performance cannot be increased or has uh, uh, upper bound.
Thank you, sir. Sir, I'm your junior student, PhD student in IIT Roorkee. I'm
Oh,
with you here.
yeah,
And
hi.
guiding Dr. Rajesh Yogi and colleagues in our
Oh,
institution.
nice, nice, good to see, good to hear you, but I cannot see.
There
Let
is
me.
outline meeting. So I'm just hearing.
Yeah, so definitely, I think I'd love to meet you guys in person also. So in case if you get any time to visit Goa, come.
Sir,
You are
sir,
okay.
our director is also from IIT Goa. I think Professor is there. Immediately.
Oh, nice, nice. So hello to everyone, but I I don't know whether camera is on or not. Let me see.
Thank you, sir.
Yeah. So any further questions you have, participants?
Yes.
Yes, yes, please.
वहाँ पे
Is it what data set?
नहीं नहीं detail बाजू में आना पड़ेगा
नहीं जाने दीजिए बंद कर दीजिए बंद कर दीजिए
So a variable data set, you mean?
Is it a ready-made data set
No,
or
no, we are creating it. I mean, because these kind of scenarios are not there, so the data sets we are creating by ourselves and annotating it. But annotation takes a lot of time, so we use some parallel processing so that it can be annotated. Or we are using some kind of semi-supervised learning approaches to annotate those data set and then train it to improve the accuracy of our algorithms. So yes, it is in-house data sets. We have there is no ready-made data sets available till now, at least, but later we are going to release some of the data sets for research community also.
and the Raspberry Pi is sufficient for handling those
Yes,
data?
for these kind of tasks, say for example in our case for object detections, we are using a nano version of YOLO and the modified version of our own algorithm, which we call it as a hype YOLO. So these algorithms are way much efficient to be executed on the Raspberry Pi, but we also have a nano Jetson deployed onto our drones.
And these algorithms you are seeing, I mean, its description is available.
Madam, please come here. Otherwise,
Pardon?
I will do
सुनाई
that
दे रहा
mic.
सुनाई नहीं दे रहा सुनाई दे इट्स वर्किंग सुनाई दे रहा कहाँ जा
Sorry, I couldn't hear the last part of the question.
Yes, the videos you were saying regarding
Yes.
that road preparation, it is available. So where they are available?
The processing, you mean to say?
Ah, yes.
Yeah, the processing, the video I showed you that the drone was on the top and then changing its head. So those are all on the drone itself.
Online they are available, you were saying.
Pardon?
Is it available online, sir?
The algorithms, the machine learning algorithms are not available, but designing a drone and the minor like flight controllers and other things algorithms are available on the site,
On the side. Okay, sir.
but not the machine learning algorithms. Only the flight controlling algorithms and some communication algorithms are available, and the list of components we are using for to design our drone from the scratch, that is available. A video is also available for that.
Okay, thanks.
Yes, thank you. Any other question?
No, sir. Just a
Okay,
second,
sir.
sir.
Yes.
Uh,
So, on behalf of Computer Engineering Department, Sardar Patel Institute of Technology, CDAC, and NSM Nodal Center, Walchand College of Engineering, I Dr. Pramod Bide, on behalf of Computer Engineering Department, thank you, Dr. Sheetala Prasad sir, for enlightening session on high performance computing in artificial intelligence and computer vision domain. And definitely, this session is helped for all the students, right, regarding the research and the current state of the art which is going on in this field. So, thank you so much, sir.
Thank you.
As a token of appreciation, we offer a virtual moment to you, sir.
Thank you very much. Thank you very much, and thank you for inviting me too.
Yeah,
Thank
thank
you.
you so much, sir. Thank you so much.
Thank you. Thank you.
Yeah,
So I'll take a leave, and all the best for your next sessions.
yeah. Thank you so much, sir. Thank
Thank
you
you.
so much.
Thank you. Bye.
years as a professor. So he is a convener in Industrial Testing and Consultancy Center in Institute, Center Head, Nodal Center Head for National Supercomputing Mission in the Institute, Chairman of Walching College of Engineering Informatics Center, in charge registrar. He is the head of IT department from 2004 to 2015. Visiting professor at Vienna University of Technology, Austria, and he is a faculty in Walching College of Engineering till then. Now, sir has completed. Might I use? Sir has completed a PhD from Shivaji University in 2005, Masters from IIT Mumbai in 1999, and Bachelor's from SGGS Nanded 1988. Sir has guided more than 6 PhD students. Sir has various membership, professional society membership, IPDPS, CCICI, and he is a lifetime member of Computer Society of India. Sir has various achievements and research awards. Sir has received Intel Micro Grant Award in Thread Safe Data Structure in 2011 and National Science Foundation Technical Committee on Parallel Processing NSF TCPP Early Adopter Award in 2013. Sir has received postdoctoral research at Computer Science in University of New Brunswick, Fredericton, Canada during April 2007 to June 2007. Sir has completed successfully project sponsored by Naval Research Board of Defense Environment for Scalable High Performance Computing, US 5 million research funding, visiting fellowship for research work at Center of Development of Advanced Computing C.DAT Pune in India in 1997. Successfully completed All India Council for Technical Education AICT India funded R&D project titled Parallel Processing and Distributed Computing and Fractal Video Coding. Received University Grand Commission Postdoctoral Research Award in 2007. Sir has published and presented many research papers in national and international conferences and journals. Sir has led various institutional leaderships, instrumental in receiving CUDA Teacher Center CTC status for the institute from NVIDIA in 2014 with fellowship with USD dollar 2,500. Sir has received Best Teacher Award at undergraduate level in the institute in 2012-2013. Sir has completed industrial sabbatical project on PostgreSQL analysis as Campus Connect program of Infosys during May-July 2006. Sir has been conducting and taught various courses at undergraduate and graduate level. And sir has even taught for MTech and PhD students, and sir has taught computer algorithms, software computing, parallel computing at undergraduate level, and advanced computer and algorithms and high performance computing at postgraduate level. So put your hands together and give a round of applause to Dr. D.B. Kulkarni sir. Over to you, sir. आवाज का येतोय? It's because of mobile?
Hello. Okay. So thank you very much, Bide sir. Thank you for introducing me. Don't sway away by this long introduction. It is whatever I did from the first day when I joined the institute. Probably everything was written in the resume, and he has read everything. Important thing is. I'm basically a teacher, and of course I'm working as a teacher for a long time, and fortunately I got a chance to work in the institute where I myself learn many things. Of course, I'm learning it still, and I hope that I'll continue to learn. During my entire journey of this teaching, there are some my students sitting, Bhautankar sir and Dage sir is also there. I started my journey with very basic things in computer science. Of course, my background is not computer science. As he has stated, I completed my bachelor's degree in 1988 in electronics. So, when I joined the institute, our appointment, of course, was in electronics department. That time, it was just electronics plus computer science. A combined department was there, and we joined as faculty members, lecturers, basically that time. That too because I got admission for PG program, ME in electronics, and then I completed that ME in electronics, and during the completion, I got a chance to get recruited on regular basis into the institute. So I started my journey of teaching. If I remember well, I started teaching basic electronics, or it was called as EDC, electronic device and circuits, and so the journey was, of course, I was knowing something out of it because I had that degree. But later on, I shifted. I started teaching C programming language. Before that, I got inducted into a committee which was responsible for computerization of all mark sheets of the university, Shivaji University. And there I got acquainted with the people who were working on basic programming. That time basic programming was very popular. And then we developed a program which actually used to calculate the degrees, calculate the mark sheets and assign the percentage, grade and everything. So there the actual journey started, and our management that time thought that this person is more oriented towards computer science. So when the division of computer and electronics and computer happened in the institute, they switched me to computer science department. And then I thought that now I should learn something related to computer science, though electronics is very essential part of computer science that time, and most of the subjects in computer science and electronics were almost same. Maybe in the final year they used to have hardly one or two different subjects. And so I started my journey. I taught C programming then, and lot many things I did. And then I realized that though I'm teaching computer science, computer science related subject to the students, basic degree is important. That's what I thought that time. So I decided that I should go for MTech in computer science, though I had completed MTech, ME in electronics. And then we had an opportunity of going to the institutes like IIC, IITs and equivalent institutes. Through QIP, we had a program, quality improvement program. So I got admission in IIT Mumbai. I completed MTech in computer science, and then I learned many subjects in computer science. And then I came back, I joined the institute, and then started my journey, completed my PhD, and then went for postdoc, and then visited a couple of countries, delivered some lectures. And the meanwhile, I developed some skills which are related to this. And then one day maybe I came across a program which is run by CDAC. It was on a workshop or training program on parallel programming. And there we learned, maybe long back, 15 years back maybe. And there we learned what you are learning now is OpenMP and MPI programming. So we had undergone some practicals, and that time, if I remember well, Professor Dr. V.C.V. Rao was there, was teaching these, was handling these subjects. And then I started my journey in parallel programming. So here important thing is I switched from time to time, and then I realized that this could be more important things to me. And then I realized that then, of course, I did some work in parallel computing, and then I submitted a proposal to DRDO, and I could seek a grant of around 50 lakhs for the research project. I completed that project, and then we thought that instead of making this awareness amongst only few people, why can't we introduce these into the regular curriculums of the students, like undergraduate students or postgraduates? So what we did is we introduced one of the subject of parallel computing in MTech IT. We started that time MTech IT in our institute because MTech CSE was there. We started MTech IT because I was shifted to IT department then. So my journey is from electronics, computer, IT. I don't know where I will go now. But because I was head of the department that time, we started MTech program in IT. And because I was head, I had a lot of powers that time. So I introduced this as one of the elective subject in PG. And we thought that it is better, and we got the feedback from the students that they are learning quite a new things. And then we slowly introduced it into the UG curriculum. So we introduced initially in third year of IT, and then we have expanded. I will tell the details later. So this is how it has all happened, and slowly, because of course, that time also when we started the project, NVIDIA was quite new. NVIDIA, we could get some grants because they were trying to sell these technologies into across all nations, and they thought that better to provide the exposure of that technology to the faculties, to the institutes. So they had many programs, and one of that program was giving grants in terms of hardwares. So we could get that grant and we could get the hardware into the institute, and because of which we could start the hands-on sessions for the students. So that is how it all started, and then we slowly developed it further. And through various experiments, through various inputs, through various feedbacks which we collected from the students, we have established it into the curriculum. And it's not just end of the game. We are still working on it. We are still trying to introduce it at the appropriate level. Of course, I'll be discussing that in detail when we look at the syllabus. But I'd like to first of all give some focus on why it is necessary that one should learn parallel programming. What is the importance of parallel programming? Of course, I'll not take much time, but the importance of parallel programming into the curriculum is very important. Everybody must get convinced why parallel computing is essential. Of course, through various sessions which were held till now, you must have realized that it is very important. But let me just tell you that these technologies are have become integral part of our life. So, for example, if you look at your mobiles, even these mobiles, they don't have very simple hardware configuration. Probably many of them have multi-core configuration. Like in case of computers, we say that it's a dual core or quad core. Similarly, our mobiles also, whatever CPU it has, whatever processing unit it has multiple cores into it. Now the thing is that if you want to use them properly, or if you just write a program and run it on our normal desktops, what will happen is it will use a default core which is assigned to it or which is available. But if you really want to make use of all the resources, like all the cores which are present in the desktop, then you should know these techniques of how to write a specialized program which will take the advantage of all the resources, all the cores, all the sockets which are present. So for that one needs to know all these programming language. Okay. So initially it was just about multiple cores, then it went to multiple processors, then it went to additional small or tiny processors, which we nowadays called as covered under CUDA programming. And basically all these courses covers parallel programming in three different domains. One is called as OpenMP, which actually looks into threading concepts, or which uses the shared memory interface, shared memory architecture. Shared memory means you have a shared memory resource which is being utilized by many cores. Okay. Second approach is where you have multiple sockets, multiple CPUs sitting, or there are multiple desktops like this. All these desktops are connected to each other. And if I want to run a program, I want to run it not only on one machine or set of machines, I want to run it across all machines. So all these machines must understand one language. They must know that how to distribute the work and who is responsible for doing what kind of work. So the division of work is very important, and then it should know that this much part I need to do, and then once I complete this part, I should communicate back to the manager, and the manager will ultimately collect all these results together and then present it to the user. So this is basically a distributed memory wherein we have every processor has got its own memory. And then what came is because in many applications we will find that the actual computations which are carried out, for example, if you take a very simple example of matrix multiplication, what is that we are doing in matrix multiplication is the basic operation is just we are multiplying two numbers. So if this multiplication of two numbers is assigned to a processor, then probably we will be able to parallelize the entire operation. Now this processor, because now with the advances of this can you just make it, yeah. Because of the advances which are made, as I said, there is a provision that you can use very small or tiny processors. So if you look at the add-on card, NVIDIA add-on card, you will find that it has got more than thousands of tiny processors. Now why they are tiny is because they are limited in capability, but they can do wonders, because if you look at the example of ants which are building a house, so you will find that their capabilities are very limited, but they can do wonders. They can build a complete nest in one night, okay, because they are huge in number. So the same principle is applied here. You have a hardware which consists of lot of small cores, lot of very small cores which have got limited capability with them. But because they are huge in number, we can make our operation, we can make our program distribute the work across all these processors and make all these processors work simultaneously at the same time. And then the work which is carried out for us will be tremendous. We'll be able to complete the work very fast. Okay. So that is the principle behind using this. This is called as many core. Okay. Earlier it was multiple computers were being used, then multiple cores were being used, multiple cores, multiple computers, and now many cores. Many cores is basically they are many in number, huge in number. Okay, and then there is a possibility of connecting more than one card to the system, wherein you will have not just thousands but lakhs of tiny processors. Now, if you look at the examples of presently available supercomputers in the list of top 500, I think somebody must have mentioned this top 500 list. Have you gone through that? So just note it down. Top 500 is the website, top500.org, is the website which actually gives you the current top 500 supercomputers in the world. And these supercomputers are based on how fast they process the work. And it is majorly calculated in terms of number of floating point operations carried out per second, or it is called as flops. Okay. So nowadays we are running into petaflops of operation, like that is multiplied by 10 to 15 floating point operations. You can just imagine how many floating point operations can be carried out by a supercomputer. Now, another interesting story behind it is, as far as the power consumption of these supercomputing stations are concerned, the power consumptions are very huge. So you can just imagine that, or you can just consider that the power consumption of supercomputing station will be, or it will be consuming almost the power which is consumed by small cities, small districts like maybe Sangli. So power which is consumed by Sangli is being consumed by one of the supercomputing stations. You can just imagine how much power is getting dissipated, is used by these processors. Okay, so if you are using these kinds of this much power, then you should also ensure that they are doing some useful work, and some useful, the important applications nowadays which are being run on the supercomputing stations are weather forecasting, and then lots of finance related calculations, then biomedical, genome related applications. I'll just be showing some of the slides based on that. So let me just go through these slides hurriedly, so that we'll see what is the importance of this parallel computing. Okay, next please. So these are the earlier parallel computers, simple computers rather, yeah. You look at this particular graph, which actually shows the speeds of the processors. Earlier it was calculated in terms of operations, but then it was switched to flops. Flops is floating point operations. Floating point operations is multiplying two floating point numbers together. So that is a floating point operation. So these many floating point operations, it's almost 20 to 85, it is somewhere here, 10 to 16, 10 to 18 almost. Okay, it's in terms of teraflops. Now that is what is written here, floating point operations per second, and used as a measure of performance of supercomputers. Nowadays we are somewhere here, teraflop is 10 to 12, peta is 10 to 15, and exa is 10 to 18. So we are in the era of exaflops, 10 to 18 floating point operations per second. Okay, and then probably we'll enter into zeta and iota. So top 500 supercomputers probably will find that they are in this particular region, 10 to 18 floating point operations. Okay, so top500.org site will give you the words, and this list is always updated, and there is always competition of who will come first. So the present, next please. So the current top supercomputer in the world is Capitan, which HPL result of 2.8 exaflops. 2.8 exaflops, so 2.8 into 10 to 18. Okay, these many floating point operations can be calculated by that system. So you can just imagine how many computations are being done. It is installed at Lawrence Livermore National Laboratory, Department of Energy, USA. Next please. So these are the top supercomputers, 1 and 2 I have given. Both of them are in USA. You can just look at this figure. The number of cores there are 1.1 crores, you can imagine. So it is spread across multiple buildings, and they are connected to each other. So 1.1 crore cores are there. 1.1 crore cores. So if you are executing a program on all these cores simultaneously, you can imagine how big your program is. Okay, so they have very huge programs which they normally run. Second is Frontier USA, 90 lakhs cores. Floating point capacity is 2.2 exaflops. Look at this figure also, 30 kilowatt power. 30 kilowatt power is being consumed by the first top ranked supercomputer. As far as India is concerned, we are at 136th. Airavat, which is installed in C-DAC Pune. Number of cores are 81,000. Flops capacity is 14.40 petaflops. ARCA at IITM. IITM is, I think it's in Pune again, Indian Institute of Tropical Meteorology, having 2.9 lakh cores. Flops measurement is 8 petaflops, and power is almost 1K. And then at 189, we have Arunika at NCMRWF, it's microwave station. Next please. So these are some of the applications which actually uses these kinds of supercomputers. So atmospheric science, then earth science, space science, next please. Life science, nuclear science, nanoscience, crash simulation, aerodynamic simulation, structural analysis. These are the emerging areas which are very close to HPC. One is quantum computing. They are also used in computational finance, in cybersecurity, in healthcare. Next please. So these are the emerging trends like neuromorphic computing, which is now a hot trend. green HPC. As I said, green HPC is basically, you have seen the power which is consumed by the supercomputers. It is in terms of kilowatts. So they have started thinking on why can't we develop resources, why can't we develop the hardware which will require less power, but at the same time it will compute more. So that is called as green HPC. So it is also named as carbon aware computing, efficient, energy efficient AI, liquid cooling. All these things are some of the important features of these green. So what they calculate is how many floating point operations you can carry out in 1 watts of usage of the power. Okay. So there is another site, green HPC, which will give you the list of top 500 green supercomputing stations. So these are more, we can say, energy efficient supercomputers which are present in the world. There are other areas like Edge AI, federated learning, HPC user scheduling, digital twins, AI simulations, AI augmented smart security in HPC, and accelerations like which are used in GPT, LLMA, BERT, and AI augmented supercomputing. So we can say that these are the trending areas nowadays in HPC, which are very close to HPC. So those faculties who are interested in doing PhDs or postdoctoral work, these are the areas wherein they can pursue these areas further and get acquainted with them and then decide their domain of research work. Next, please. So let us look at basics of supercomputing. It's a large collection of processing elements that can communicate and cooperate. Yes, next, please. So these are the definitions given by some of the people. Next, please. I'm just moving ahead, like moving fast, so that we'll try to give brief information or very short information about all these things. There are some paradigms like concurrent programming, parallel programming, and distributed computing. Concurrent is basically you have one processor, but one processor is capable of executing multiple programs simultaneously. So we switch between these programs. The processor switches between these different programs. Parallel is you have multiple processors available, they are executing different programs, or the same part of the program are being executed on them. And distributed computing is again same, but only difference is that in distributed computing you have multiple machines, multiple physical machines available on which the program is being run. Next, please. As far as distributed computing is concerned, we put them into a cluster. Now this may be called as a cluster. To make this as a cluster, we need some installations. Okay, we need to install the software. Examples of the software are, I forgot it. Let me just recall it. Maybe once it is recalled, I will tell you. So there are some standard software, open source softwares which are available, which needs to be installed on all these machines. So in that case, what will happen is one of the machine probably could be manager, and rest of the machines are workers. So all those who are connected to this network in the entire campus, they will be able to submit their work. Work is basically a program. So they will be able to submit their program to this machine. This machine in turn will spread that program, part of that program, to every worker. It will divide that work, it will assign that work to every node in the cluster. And then the cluster, every node in the cluster will complete the work which is assigned to them and submit the result back to this manager. Manager will compile all the work together and then present it to the user. So that is how the cluster will look like. Yeah, yes, similar to Hadoop. Only thing is that here the systems are different, physically distinct.
Is it operating system same from all the?
Operating system, basic operating system is same, but you need to install that software.
Okay, the same operating system is required from all the.
Yes, yes. Most of the machines should have same operating system. What we have done long back, I mean, maybe 10-15 years back, is we have installed a small cluster, some four machines and one manager, and we have installed that software. Now, why that special software is required is because every machine should give the authority to this particular manager, that this manager is capable of dividing that work and assigning that work to individual machines. Second thing is, they must be secure enough so that the communication happens between these two machines. This machine should be able to identify that who is getting the program, the workload, and who is submitting that workload back, I mean the results of that workload back. So for that, the encryption kind of technology which is being used for data, delivery of data, programs and the data, that is important. So for that you need to first of all prepare the complete infrastructure, the framework, and for preparing that framework, this software installation is essential. Okay, so we need to install that software on all the machines for which you are forming a cluster. Yeah.
In that case, suppose I have a data set, large scale of a data set. So that data set should be required on the server side. Okay.
Yes.
So is it like that then that machine is going to send that data set to every machine?
Yeah. One thing is you can send the entire data set to every machine. Normally this doesn't work because the data set itself is so huge that sending that data to every machine will take more time. So what this as a manager will do is it will divide that work, divide the data also appropriately, and then assign only chunk of that data to every machine. So first part probably will be assigned to machine 1, second part is assigned to machine 2, because in most of the cases the program which runs is same. So program gets shared and the data is assigned to every node. So there is only movement of data from one node to the other node. So this machine being manager, it will send the first chunk of data to workstation 1, second part of the data to workstation 2, and so on and so forth. So it will divide that data and then it will tell them that execute the program which is given, which is shared, execute it on the data which is given to you. And then every machine does that work and then completes and submits the result back to the manager.
So is it any for specific like operating system? This can be software for only
No. As far as I know, we have done it only for Linux. But Windows probably they also have similar kinds of setups. Ubuntu is Linux only, no? Yes, very much possible. Any?
let's say, is it required for specific language like Java only?
No. Yes. We have done it successfully for C and C++. So we can very surely say that this is very much possible in C, for at least programs in C and C++. We haven't done it for Java or any other language. So you can, whatever old machines, if you have old machines available, you can take those 4 or 8 machines together, you can take the entire lab and then set up a cluster. And then one of the machine could work as a manager. So you'll be able to execute MPI kind of jobs on this machine, on this cluster, very easily.
So we are eager to view that demonstration on
Cluster, that we can do, but it will require some time. Setting up of the machines will require, maybe you can look for I'll tell you the name of that tool. I forgot it.
Gangila is software that
Huh?
Gangila. That is your manager.
Yeah, that is also a manager. That is through that also we can do it. Oscar is one such software. Just note it down. Oscar. Oscar is the software which actually allows you to set up this cluster. Yes, it is a part of that. All right, next please. So this is about the software stack, which probably is already covered by the other speakers. Next please. These are some of the components of the supercomputer. I don't think, yeah, this is how the server setup will look like. And these are the rack mountable servers, rack servers. Yeah, this is what multi-core CPU is. You have multiple cores available, and then it is connected to a bus interface, and then you have you carry out your work in terms of multi-threading applications on this. Next please. Next please. Yeah, this is just a minute. This is an example wherein we have multiple processors, sockets available on the same motherboard. I don't think we have these kinds of setups, but probably the workstation kind of setups have this architecture. Like you have multiple cores, you can see those cores on the motherboards, 4 processors or 2 processors. So there we can execute MPI programs. Or the simple example is this kind of the clusters, wherein we have physically distinct processors, physically distinct machines which are connected through network. Now again remember, whenever we are talking about parallel programming, though we are trying to get the solution to the huge computational task which we have, the overhead of this is, or the disadvantage of this is basically the communication time. So we divide this, the performance, or we look at this performance of parallel program, and that is affected by two things. One is how many computational elements you have, and what is the kind of communication which is required between these processes. So communication overhead and computational overhead are two important things. Now when we talk of communication in clusters, because these machines are independent, these are physically distinct machines, the communication time required is more. Of course, the performance will be calculated by a summation of computation time plus communication time. So if that communication time is more, then probably your performance will go down. Though you have multiple processors available, but it requires, they need some kind of communication. So when we write a parallel program, we should ensure that the communication requirement between the multiple processors is as minimum as possible. If you have more communication, then it will take more time, and ultimately the purpose for which you are going for parallel computing will be lost. So though you have huge number of processors available, because the communication time is more, probably you will not get the advantage of parallel computing. So communication overhead is one of the major problem in parallel computing. You need to avoid, you need to minimize that communication overhead. For that, what we can do, as I said, as far as communication between processors are concerned, whatever networking technology we are using, that networking technology must be very fast, as fast as possible. So instead of using simple cables, you use Ethernet. Instead of using Ethernet, you use fast Ethernet. Instead of using fast Ethernet, you use fiber. As far as single machine is concerned, you must have heard that as far as the particularly as far as the CUDA programs are concerned, what architecture we have is, we have a desktop, a CPU and an add-on card, NVIDIA add-on card. So the communication between, so whenever you are writing a program and executing it on CPU, the part of the program actually gets executed on that GPU card. Now when you say that it is getting executed on GPU side, whatever data you have on CPU, that must be transferred to the GPU. So the time taken by this transfer process, transfer of data from CPU to GPU, and then again getting the results back from GPU to CPU, this is very critical. Okay, so there also the communication time, we can call this as a communication time, because it's a communication between CPU and GPU. This is very, very important. So there are lots of work which is carried out on how to reduce this communication time. So we call it as host and device. So sending the data, sending the information from host to device and device to host, it takes huge amount of time. Where your computation is concerned, these computations are taking very, very little time. But the transfer of data is taking more time. So you should be very careful while writing these parallel programs, that you should ensure that the transfer time is as minimum as possible. Now again, we can take a very simple example of parallel program, wherein if you want it to be parallel, you should be able to divide that work into very small units and then assign these units to the different processors. Now if you make it very small, what will happen is, every processor will do some work and then it will require some data from some other processor. Similarly, the other processors will also require some data from some other processors. So that will eventually melt down to huge communication between the processors, and ultimately the performance of the overall program, parallel program, will go down. If you make it very big, ultimate extreme end is you have only one processor which is doing everything. So again the performance is very, very badly affected. So what we want is, we want a balance between these two. We don't want those tiny methods, tiny programs to be executed on single processor. At the same time, we don't want everything to be executed on single processor. So we want somewhere in between kind of thing. So that's why this writing a parallel program and getting the performance from it is very, very critical. You need to decide how big is your process, how big is your task, and then depending on that, it will give you the performance. You want some kind of communication, but at the same time, you don't want huge communication. You want some kind of computing, but you don't want it to be very, very small. Okay, so lot of things which are required, and probably that will be covered in one of the standard textbook which is being used by Anantagrama. It actually tells you how to write a parallel program and how to calculate the, theoretically at least, how to calculate the performance, what maximum performance you can get from a particular architecture of parallel computing. Next please. Anantagrama. Anantagrama, Parallel Computing by Anantagrama. It's a very standard book. Yeah, this is how the dual socket I said. There are two sockets. One is this. So two physical processors you will be able to see on the motherboard. Okay. So this is multi-socket system. Next please. This is the typical many core architecture, GPGPU architecture. You have this is multiple cores are available in the system, and then it is getting connected to, you can connect it to the GPGPU. So this is the distributed memory model, and this is how the GPGPU card will look like. Of course, the expert sessions will be covering all these things in details. Please, next please. Advantage, thus or save time, that's okay. Next. Making use of HPC. Next please. Next please. Yeah, these are the techniques which probably will be covered in the various aspects, MPI, OpenMP and CUDA programming. Next please. Yeah, you can just go through slowly all these slides, remaining slide. Okay, so these are the different ways in which we can write a parallel program, and what exactly happen when we execute the parallel programs. Next please. So these are the different methods which can be studied. Next please. The pipeline model, process farm model, then the concurrency, scalability, locality and modularity. All these are very, very important. Of course, we are not going in details. I am assuming that the other speakers will go through it. We are writing a parallel program, distribute the data to the memories, distribute the code to the processors, organize and synchronize the workflow, optimize the resource requirements to make it efficient. And these are the three techniques. Next please. OpenMP, MPI, and there is one more platform called as OpenSCC. Probably you must have heard of it, but once you complete this course, FDP, and go back, just look for this OpenSCC. It is again a platform wherein you can write a parallel program and then you can execute that program on any architecture. We know that there are various architecture by NVIDIA, architecture of Intel, architecture of AMD, and so on and so forth. So instead of writing a special programs for this, you can write one program in OpenSCC and that gets executed on any one of these hardware. So we can say that's completely independent of the hardware on which you are running your program. So you do not worry about writing a program, different versions of the same program for executing them on different platforms. Next please. Yeah. All right. So this is all about general information of what HPC is, why it is important, and if you have any questions.
Sir, my one basic question.
Yeah.
We have to create a cluster with a different node.
Different?
Nodes. That is, we have to say the cluster is node.
Yeah.
And every server, we have some GPU. So suppose say my one node is a 4 GPU, another node is 4 GPU.
GPU or CPU?
In that machine, there is some GPU.
Mm-hmm.
Okay. So if I write some hybrid program or MPI program, can we utilize all these 4 GB to 4 GB, 8 GB simultaneously?
That is possible, or otherwise NVIDIA has given some extensions. Yeah, they have written some extensions in which they have said that you can have communication between the different GPU cards. So you can connect the multiple cards to each other, so that the communication, instead of happening with CPU, it will directly happen with GPU. I hope you are understanding. There are two, because this GPU card sits in PCI slot. So there are multiple PCI slots. So what I will do is I will purchase multiple GPU cards, put them into these different cards, different slots, and then connect them directly through some wire.
But it is like a single PC. It is
No, it is not
Same
distributed.
machine, we
Yes,
also install
yes, yes.
two memory card is the two GPU card. So it is like centralized.
Yes.
Okay. So my question is, if you have to, this is like a some PC,
Hmm.
and we have to install now my PC with GPU card.
Hmm.
Like we have say cluster, we have to increase the performance with the core.
Yes,
We
yes.
have to connect it. So my question is, can we utilize all these GPU?
I-
Say that 2 GB, suppose 5 machine, 10 familiarity, and we have to increase all these 10, like mostly machine learning program, deep learning program, they require the GPU. So can you say that combined GPU?
If I understand your question, what you are saying is it possible that we use GPU technology or CUDA programming on a cluster? On cluster, I don't think, I haven't seen any such example, because there we are using MPI basically. And MPI what?
Use the performance of that system. But my question is, can you use that GPU also?
No, to use that GPU, what you can do is you can put all those cards on one machine, and then you can use that machine.
There is only 2 slot machine. There is some limitation.
Yes, yes, that will be there. But I haven't seen any example wherein they have used this kind of architecture. No, but he is trying to combine both. That is, he is making a cluster of all the machines, and every machine is having GPU. So that is, I haven't not seen. But there could be some examples. Huh? Probably the supercomputers which they are claiming, because they don't tell you what is the architecture through which they are connected. So probably they must be using the similar kind of architecture, wherein they have multiple processors available, multiple physical systems, and then every physical system has multiple cards, and then they are connected in a cluster. Yeah, they use InfiniBand. InfiniBand is basically a networking technology. Yes, high-speed networking technology. So normally in clusters, they don't use this Ethernet kind of connections. They use InfiniBand only, which gives you better performance in terms of communication. Okay. All right. So our task is basically to see how it can be incorporated into the curriculum. So let me switch. Yeah. So before we go through this, if any other question is there? So as far as your desktops are concerned, you can think of many of the desktops nowadays, or many of the laptops even, have this GPU card. So you can install those GPU cards on your systems, and then you can check, you can write very simple CUDA programs and test them on that local system. Another way is you can use the tools like Colab, Google Colab you can use, and then you can execute your work there. Third option is you can use the AWS platform. They provide you complete HPC hardware setup. So you can create an instance and then get that kind of setup attached to your instance, and then you can execute your program, your workload there. So these are different options which are available, or you can do it on your desktops. Many of the desktops nowadays have NVIDIA cards. Okay. As far as MPI programs are concerned, a cluster is required. Of course, you can get that cluster on Amazon Web Services also. But if you set up your own cluster, probably that will be more, that will give you a better experimental ground for carrying out lots of experiments. And you can give it to the students community also. They can use it, because anyway it is available with 4 machines or 8 machines, and those machines will be old machines. They will understand what is the importance of parallel computing and what happens. They will be able to compare the performance of one system versus multiple systems working simultaneously. Okay. And the simple programs which could be assigned to them or which could be given for experimentation is matrix multiplication. You can divide the work very easily. There is a communication happening between the different processes, and they will come to know what is the speed up they get, how fast they can carry out this particular work. All right. So let us now switch to why it is important. We have seen why it is important that we should have this parallel computing into the curriculum. Now see how and where we can introduce these parallel computing. Can I get some water? Water, can I get? I think, let me show. Yeah, I have it. Just a minute. Yes, any question?
My question is basically on the performance of an application,
Mm-hmm.
not an HPC.
Mm-hmm.
If I consider AWS services for EC2 deployment of my application, and I have a huge application, enterprise level application, and it has different modules like authentication, it has user, and then admin, different modules in it. And I'm going for a modular architecture.
Okay. Mm-hmm.
So is it better to have all these modules in one EC2 and have load balancing for the performance, or to deploy it on different EC2 instances for better?
It is better if you have multiple instances available. Like, see, many times whatever parallel we are thinking of, if you are considering the CUDA architecture, then we assume that all the cores, all the tiny cores which are executing these processes, they get a similar program. And remember that if they are getting a similar program, then only the performance will be better. The program is same, the data is different. If they are working on altogether different programs simultaneously, I am saying, if they are working on completely different logic, then the performance will not be good, because it works in form of warps. Warps are basically 32 threads being computed simultaneously. So if their programs are different, then the performance will go down. So what we want is, because you have parallelized it, but because your modules are completely different, so it is always better that you push one module. Of course, you need to look at the, you need to carry out dependency analysis of it. You need to check that one module is not depending on other. Then only you can run them in parallel. So suppose that you have identified that you have 4 different modules in a program which can be run simultaneously. Then you can assign this particular module to one processor, another module to another processor, and make them execute simultaneously. It is always better. But if you try to push them in form of or into one instance, then probably it will not give better performance, because you are pushing all 4 modules on one particular instance, and one particular instance will have only one set of cards associated with it. I hope you are understanding. GPU cards, basically. Okay. So this comes under whatever is called as dependency analysis. So all these important information about how to design a parallel program, that will be covered in Anant Grama's book. Okay, that is a good book for theoretical thing. But as far as normal parallel programming and parallel processing is concerned, you can write simple programs. As I said, the simplest program is matrix multiplication. So try to run that matrix multiplication program in using OpenMP, then MPI, and then CUDA, and try to get the difference. If you could do this much, then it is more than enough. And if you showed it to the student, probably the students will be able to take it to the further level. Okay. But these things, the difference between these programs or these technologies is very important. Okay. All right. So as I said, we thought of introducing this into the curriculum. So we thought that better we introduce it initially to the PG students, because that time parallel programming was out of question as far as the syllabus was concerned. It was not there in even IITs that time. Okay. So we thought that let us try to introduce this subject for PG students, and that too as an elective. Of course, we had made it compulsory to all, though it was called as elective, it was compulsory. And yeah, we have assigned it to, there were some 12, 18 students were there. And then we have given it to them, and then at the end of that we took a feedback, and they were very happy with that, because it was a new subject, new concept, everything was new. And that time we had established that the cluster using Oscar, and we found that they were taking a lot of interest in writing very small programs and getting executed on that cluster, and then identifying that this is really a good platform. a parallelization they can see it. So for engineers or for practitioners, very important that instead of telling them into theoretical knowledge, if they can translate it into actual practical knowledge, they will understand it fully. So that experiment was successful, and then we thought that let us introduce now, because we know that the undergraduate students' quality is better than PG students, unfortunately. So we thought that let us now introduce it to UG, and then we introduced it directly, because in UG you must be having the same observation. The final year students normally they are very careless. There is carelessness. They are more oriented towards getting a job and doing something, appearing for gate. And so we thought that most sincere students in the entire 4 years is most sincere class is third year. So what we did is we introduced this to the third year students, and that too as just a practical subject. So it was just a practical subject. We introduced it, if I am not wrong, it was introduced in 2012, 11 or 12 in third year. And then we say that it is just a parallel computing subject. And we covered all these three aspects like OpenMP, MPI and CUDA. So all three things were introduced to them, and it was just a practical course. One lecture was there in which I used to tell them what is MPI, how to write a program, what is OpenMP, what is CUDA. Of course, CUDA that time it was not very popular, and a lot of resources were also not available in much detailed form. So we have focused more on OpenMP and MPI, and just told them what CUDA is and what that technology is. After 2 batches, we found that students were taking interest, but they were getting confused, because all these technologies are related to parallel technology. So they were confused about what is OpenMP, MPI and then CUDA. So there was a lot of confusion because it was just a practical oriented subject. So when we conducted a feedback for these 2 batches, we have found that there is complete confusion. They were saying that it is huge burden. They were not understanding how to write parallel program, which approach is to be used, how it is to be executed and all that. So we realized that there is some problem. So we thought that instead of giving it as one bundle, let us divide that bundle. So we said that let us divide it and let us initially give this as OpenMP, simple threading process, which they can test using OpenMP, and then MPI, wherein multiple computers are working for the same program, multiple physical machines are working for the same program, and then in the next semester, probably they will see what CUDA is. So that is what we did maybe in 2015. So we have divided it into OpenMP, MPI and CUDA in separate semesters, and that is the thing we followed for a long time. So it was, what we did is, as far as the current thing is concerned, we have in second year we cover OpenMP, and the third year first semester we cover MPI, and the third year second semester we cover CUDA programming, okay, GPU programming. So I'll show you that. These are some of the technologies which are coming up, like different kinds of processors. One is called as CPU, then GPU. Nowadays you will see TPU also. Then DPU is also coming, and QPU. QPU is quantum computing. Of course, probably that's the future of this parallel computing. Next, please. So this is the architecture of multiple processors and GPU device. Probably this is repeated. Next, please. Yeah. So these are the different approaches which one can follow. Like one can say that this is not required. So probably a lazy person will say that I will not be introducing anything as parallel programming because this is a very high-end kind of topic and this is not required at all. So that is one approach. Second approach is adaptation. Adaptation is you are trying to mix. It's like you have bunch of cards and then you are adding some of the subjects, like OpenMP as one of the core subject, MPI as one of the subject, and CUDA as one of the subject. And the third thing which actually we expect is adoption. Adoption is, it is basically not a separate subject as such. It is basically the thought process. Parallel programming is a thought process. So as far as our human brains are concerned, we are doing many things simultaneously. Like when I am talking, I am walking also. So my brain is trained in a such a way that I can do both these things simultaneously, not just these two things. I am thinking what I need to speak. I am thinking what is happening to my hand, whatever. So there are multiple processes which are running. So we thought that as far as the introduction of parallel computing is concerned, it should not be limited only to a particular semester or to a particular course. It should be evenly distributed, should be part of almost every subject. But then we have identified that there are some subjects to which it is directly, it can be related to and then added to. Okay. So that's the best approach is adopt. Adopt is you are adopting to that entire parallel computing syllabus. Next please. Yeah. So this is what we are doing now. Second year, sorry. On this side it is year, and this on an x-axis you can say it's a semester, odd semester, even semester, that is first semester and second semester. So in second year, second semester we have OpenMP, exposure to the students in form of OpenMP. In the third year we have MPI. Now MPI we are not added that as a subject because I am teaching computer algorithm also to the third year students. I have taken this as one of the module in computer algorithms. Okay, so in computer algorithms in our institute, we have taken this as a third module, MPI, parallel programming, particularly MPI. And then I have asked them to implement some of the standard algorithms using parallel computing. Okay, so that is how we have incorporated parallel computing into the curriculum. And in the even semester, that is third year, second semester, current semester, for the third year students, we have many core CUDA programming. So we introduce them. There is a separate subject, a special subject, which is having one lecture and a practical, no theory paper. So there we introduce this CUDA programming, in which we ask them, we give them the different programs, and we tell them how to write a program. And we, in the lecture, we actually cover the CUDA architecture in the class. So I'm handling this subject in this semester. So that is how we are doing it, and we are doing it for last more than 5 to 6 years now, more than that maybe. And then we have thought of introducing one of the elective subject in the final year, first semester. Okay, and that is basically covers the performance related aspects of parallel programming. We refer to that Grama's book, Anand Grama's book, which actually tells you how to design the program, how to work out the efficiency of the program, the performance related issues, how to divide the work and ensure that there is least communication present, and how this communication affects the efficiency or the performance. So you can create a mathematical model for all these things, and that is being taught as, this is a theoretical course, because there you are supposed to tell, given a program, how you can convert it into a parallel program, and then how you can get the speed up of that, the efficiency, the performance, and lot many parameters can be computed out of it. Okay, so that is being covered as an elective subject in the final year. Again, as you know, the final year students are very least bothered about the content, so many of them don't take this as an elective subject. Okay, yes. Mm-hmm.
Then what about the career option, like after completion of their graduation?
Mm.
In which direction they can opt for choose the career? Whether that will be helpful in getting some job roles, or how exactly they can utilize this skill?
Yes. I think the previous session actually, I was expecting that all the things related to that is covered in that. Like, what is the use of parallel computing in actual? What is the current status of parallel computing? Like, as far as these models, Gen AI models or LLMA models or transformers are concerned, you will find that all of them are using somehow they are using neural networks. And neural network, the basic thing there is parallel computing. So if you don't have that hardware, if you don't have that NVIDIA's hardware available, then probably you will not be able to run your Gen AI programs there for training the neural network model. So as far as training the neural network model is concerned, you need to understand the philosophy behind parallel programming, because you are actually deploying that work of learning, training, uh, simultaneously to the multiple processors, and you have not limited number of huge number of processors must be there to train a model. Lot of iterations, lot of epochs and all those things. So those are happening. So you must have this kind of platform at the back end to create a model, a neural network model. Okay. So this is what we feel is this is a must for AI, for Gen AI, for transformers, for Lalma, whatever. So this programming must be known to the, of course, nowadays probably you will find libraries available. But ultimately when it comes to the actual application, deployment of actual application, you need to fine tune these models. And for fine tuning these models, you must know these programming languages. Like ultimately you will come to know that there are libraries which will actually convert these programs into CUDA programs. And those CUDA programs are actually run on the machines. So if you understand CUDA, what CUDA is, what is the hardware, the GPU hardware, how they communicate, what are the problems associated with whatever I said, the data transfer and all those. So if you know that, you will be able to fine tune the entire application and then deploy it further. Okay. So for fine tuning these applications for a particular requirement, you must understand all these paradigms. And then only you will be able to fine tune them and get the optimal performance out of it. If you are happy with single processor, then there is no use. I mean, if your application itself is it requires very little computation, then you need not worry about parallel computation and all these things. But if you are thinking of having your own model, having your own framework, having your own neural network, or having your own GI, general AI, so for those kinds of things, this is essential.
Sir, like previously we had one subject distributed computing.
Mm-hmm.
So whether the distributed computing is similar to this parallel computing or it is totally different, because in last 2 to 3 days we had learned about SIMD and IMD and
Yeah.
so that already
All those concepts, all those concepts you must have covered under the theoretical things. But as far as practical is concerned, SIMD, MIMD, all these are actually implemented in CUDA. So you'll find that the same programs, SIMD is what? Single instruction, multiple data. So same thing happens there. You'll be able to see what exactly happens when we talk of this SIMD. Single program is being shared amongst all the tiny processors. So they share this program, and the data which is available is actually given to each one of these code separately. So basically you are trying to speed up the process, entire process of execution.
Nowadays, actually, with respect to the big data,
Mhm.
everywhere we require this.
Yeah, everywhere it is being used. Only thing is,
For
yes,
handling the big data, we require.
yes.
But problem is that we are more, developers are also more focused on only supervision. They want to work on only applications.
Yeah, many of them are working on application, but now there is a need that if you really want to run, you must have seen why DeepSeek has become more popular. It is using less hardware. It uses less hardware because the models are more efficient. They have worked on software part of it. They have tried to optimize the logic. And then by optimizing the logic, they said that the same thing can work on the lower end platforms. That is what they have proven. That's the basic difference. Am I right? Why DeepSeek has become so popular? Or what is the difference between DeepSeek and ChatGPT?
DeepSeek given the concern how it will be evaluated means
Their models are more efficient. What is the model? Model is basically a software. The way in which you make the hardware learn the things. Okay. So for that you need to understand the way in which the parallel programs are written. How we can make them more efficient in terms of time. How the same program can be run in less amount of time. That is what they have done. So that is the crux behind DeepSeek. Then they said that NVIDIA kind of hardwares which are very costly are not essential. Instead, you can use lower end kind of devices which are still manufactured by NVIDIA. So it is not that they are not using NVIDIA, they are still using NVIDIA. What is NVIDIA? NVIDIA is basically parallel. They are developing all parallel platforms. I hope that
Sir, in curriculum, instead of now national education policy is there is a specific course, sir, BSc, that is a very specific course. So we introduce this course in that library. That is like in VJT IT department, I introduced this. In BSc, very specific course in parallel computing library. That we have to give us some library course, that is a specialization course. So we have to introduce that lab also.
That needs to be, that is the need of.
From this, in our curriculum, I introduced this BCSC course in parallel programming. Like I give the subject. When we see that is we have to introduce some subject.
Yes.
So we have to add this lab course in that course.
Yeah, but because the technologies are different, they must understand. They get confused if you put everything in under one head. So to make it understand.
No need to every semester only open.
No, but if you ask them to write one program, they will get confused. That is what we had experienced earlier.
So past student they do. Right now,
Present students are probably you can
learn. So their capacity is very.
See, you need to make them move ahead. Like only introduction part will not be sufficient. What is complex part in MPI, whatever complex part we have in CUDA, that needs to be covered somewhere.
That they have to, at least this,
Yeah, only matrix multiplication is only for us, for the faculties. We should tell them that they should go beyond it now. Okay, matrix multiplication is just to tell them that this is the usefulness of writing a parallel program and how they are faster as far as your sequential programs are concerned. Now they need to take this and move further. They need to look at the different applications, different standard algorithms, and then they need to parallelize those algorithms, because these are the standard algorithms which are used everywhere in every domain. So we must make them aware about what is the hardware available and how in a best way they can use that hardware, because it is not always that you will get more output, more throughput when you have a particular platform available, like hybrid programming, hybrid HPI. CUDA in case of GPGPU. Okay, so given the hardware, they should tell what is the best way we can write a program, and given the problem, they should tell what is the best hardware they will require to make it more efficient. Both the things are very important. So best utilization of resources and then making the application the best. Maximum speed up, we can say. So he should not say that use it, run it on supercomputer. You should define what exactly, which part will be put on what processor, what kind of platform. Okay. So we don't have any automatic way in which it gets parallelized. It decides on its own what is to be done on what. That has to be done manually. You need to think of the logic and then appropriately assign appropriate part of it, divide it properly, and then assign appropriate part to the appropriate hardware for execution. Okay, that has to be done manually. So for that you need to, and the student must have that understanding of what hardware and what are the limitations, what technologies one should use. Okay, all right. So let us move next. Yeah, these are the as far as the syllabuses are concerned, what we can do. Semester 3rd or 4th we can have OpenMP. Some of the things are there. I don't think I should go in details of that. I'll be sharing the slides so that you can go through those slides later. Next, please. Yeah, as far as integration is concerned, as I said, we should not take these as separate courses. Instead, we should put them into the existing curriculum somewhere. So as far as this OpenMP is concerned, what we can do is this basically a part of process and thread management, if you understood it properly. So we can put it in various courses like operating data structures and operating systems somewhere. Okay, so there we can have some integration in terms of parallel sorting algorithms, parallel search operations, dynamic data structures, and all those things can be covered in that particular subject. So if you introduce some of the points in the existing curriculum, then we can say that we have achieved complete throughout parallelism in the course. Yes, next please. As far as MPA is concerned, again, it can be introduced in either the fourth semester or fifth semester, and this is what we can do. That is what we are doing now also. Simple example assignments are matrix vector multiplication, calculation of pi. These are very standard examples. Matrix multiplication, distributed sorting algorithms, performance analysis, execution time, and all those things. There are some textbooks which are also specified here. Next, please. Now, as far as integration into the curriculum is concerned, you can integrate into algorithms basically. And if you have advanced data structures or distributed data kind of subjects, you can put this MPI into it, and then you can add MPI CH also into it. Parallel tree structures, concurrent queues and stacks, and all these things can be covered there in algorithms. Next, please. Design analysis of algorithms, you can add all these things. Next, please. And then CUDA or mini core programming, this can be added into the different subjects, but we are taking this in Walchand College. We are taking this as a separate course. We call it as parallel computing. Okay.
But it is elective course or compulsory?
No, it's compulsory. Now earlier we had made it elective, but we thought that let us make it compulsory now. So all the things we are doing in Walchand College are compulsory, except the last course which is put as an elective. So this is how the CUDA integration can be done. There are simple assignments which are there, and it can be put into different subjects, related subjects, into the curriculum. Yes. These are some of the textbooks, and then we have elective subject, which basically uses this Anand Grama's book as a textbook, and then there are some other books also. We have said that these must be the prerequisite for all these courses, because you can understand the theoretical part, but if you have practical knowledge of all these things earlier, then it will help you in actually realizing what will happen when you write a program. Next, please. So we can have this as a advanced course. Maybe this can be introduced for the PG level, as with the assumptions that they have covered parallel programming, some aspects of parallel programming in UG. Next, please. Yes, next. So this is the syllabus which is given, which can be either given to the final year students, final year undergraduate students, or it can be core course for the PG students. There are very lot of details which are this is the slide which actually I collected this information from ChatGPT. You can just see what it says, how these parallel computing contents could be embedded into the present curriculum. So this is what it says. Like there are various aspects, like foundational exposure could be given in the second, third semester or fourth semester, and what are the different topics which can be covered. Okay. As far as advanced integration, upper levels electives like third year and fourth year, these are the contents which can be introduced into the curriculum. HPC, CPU plus GPU computing, distributed systems, cloud parallelism, MapReduce, Spark, serverless computing, AI, ML, and all these things. Then, sorry, this was the advanced part. Before that, mid curriculum is third year. Sorry, advanced part is for final year. In mid curriculum, that is second year, third year particularly, we can have it as introduction to parallel computing, wherein we are having parallel architecture, parallel algorithms, performance metrics, then different models like share memory model, distributed memory model, GPU models, and all these things into the curriculum. And then the advanced course, which we have seen just now. And then as far as tools are concerned, what can be covered under this is the cloud cluster access, Amazon Web Service, Google Cloud. Then the different tools which can be used are Thread Sanitizer, then NVIDIA Insight, Intel VTune, and so on and so forth. These tools are very important, NVIDIA Insight and Intel VTune, because Intel has also now made its presence into parallel computing. These are the advanced topics like role of Kubernetes, Kate, and Docker containers in HPC. We are still working on it, and quantum computing is yet to come. Okay. So these are the some of the players which are present in HPC and AI. NVIDIA, as I said, they are the leaders. Then Google Cloud, Microsoft Azure, IBM, and Amazon Web Services. These are the services which one can use directly for conducting the practicals. Okay. As far as Intel is concerned, they have made one API, application program interface, and through this one API, this is a platform, we can write the standard programs like SYCL programs. They call it as SYCL, SYCL. So SYCL programs can be written and executed using this one API. They have separate toolkits available for this, and they claim that it can be used for writing parallel programs on CPU, GPU, and FPGAs. Then AMD has also worked on this. They have again different kind of hardware platform. They call it as Radeon Open Compute, ROC. They have their own hardware, as I said, and own software sets. The advantage of OpenACC, which we have seen just now, is, as I said, write one program using the standards of OpenACC, and then you can execute that program either on NVIDIA GPU or Intel hardware, or it can be executed on AMD's. Okay, so maybe you can give this exposure to the student. Students will understand how it will work on these different platforms, the same program. Okay, right. These are some of the tools, their features. One API, Intel One API, AMD's ROCM. Next, please. One API looks like this. You can get all this information on internet. Then AMD's software stack looks like this. And OpenACC in OpenMP 4.5. OpenMP 4.5, there is one concept called as compute offload. Compute offload is basically you are offloading the computational part from CPU to GPU. And this OpenACC has OpenMP basically. Just a minute. OpenMP 4.5 has allowed, made this compute offloading possible. Okay, compute offloading is you can write OpenMP program, and the same program uses NVIDIA GPU for computations. Okay, yeah. Lot of work, lot of standardization work is going on. You can get the details of OpenACC and OpenMP 4.5 on these different websites. There is OpenMP website available. Then as far as NVIDIA is concerned, next please. So you have some tools like CUDA IDE, then visualization tools are there. There are lots of tools available on CUDA website. Lots of certifications are also available because they are leaders. They have done a lot of work into the domain of parallel computing. So you just open that NVIDIA site, you will get lots of certifications, lots of tools, lots of frameworks which are already available. Only thing is that we should use them properly. And if you have the background of how parallel computing works, then understanding most of their platforms, whatever they are coming up, like they come up with different hardwares also. Every time this gets announced by the CEO of NVIDIA. Okay, so you will come to know that how parallel computing is important there. What are the different hardwares and platforms available? Yes, and Intel has developed this vTune profiler in which you will, because see, you have lots of cores available, lots of processors, lots of cores. So if you want to debug a particular application, or if you want to visualize what is happening at what time, because we are saying that all the processors are working simultaneously for solving one problem. So who is doing what at what time? Understanding that is very important. So that can be visualized by this kind of profiler, Intel vTune profiler. Similarly, there are some similar tools available from NVIDIA. They will help you in understanding what is happening, why the performance which you are expecting out of program is not, that you are not getting. So those things will be available. Okay, you can visualize what is happening, who is sending message to whom, what is the time taken by this particular message to reach a particular node, or why your performance is getting hampered, what is the reason. So that you can easily find out with the help of these profilers from NVIDIA or from Intel. Next. So these are some of the snapshots of the profilers. This is NVIDIA's. Then there are sets of, this is the VTunes snapshots. You'll come to know what is happening. You can get all the details. You can see this is only one screen. You'll get at least 10 such screens. You'll come to know what is a particular processor doing, what is a particular process, how the process is being handled, what are the resources consumed by each one of these processor, process everything. Okay, so this is very complicated. If you are really interested, you can just go through it. So you can see the effective local core utilization. Now, one thing reminded me about this. Now, if you want to really know that what exactly, how much resources are being actually utilized when you run an application. If you are, of course, running Linux kind of platforms, Linux kind of operating system, you can get to know about what is happening into your system on your laptop. There are some set of commands which will help you in understanding to what extent the resources are being used, and you can easily judge that how much percentage of utilization you are doing of your own laptop. Okay, so there are different commands, like it will tell you how many cores you have, to what extent every core is being utilized, how much memory is consumed by every processor. So all those details you will be able to get. There are different commands. You can just find out them on internet. Yes, next please. Yeah, this is very important. As far as nodal center is concerned, what we can do, as Walchand College of Engineering has become a nodal center, we can arrange these kinds of programs like FDPs. Whenever you go back to your institute, you can think of all these as a resources. We can have expert lectures, we can provide expert lectures, we can provide remote access. Of course, we haven't yet received the hardware which we are expecting from C.I.T. Shortly we will receive it. But once it is available, once it is installed into the campus, you will be able to get the access to it directly, remote access from your campus. Then we are trying to make one website on which we will be putting all this information, all the videos, the training material, the list of experiments, the syllabus, everything on that website. And then we are also thinking of sponsoring some final year projects with the constraint that they are all in domain of parallel computing. And then providing the lab manual, so that it's a hand-holding kind of process which we can carry out for those who are trying to introduce these as a subject into the curriculum. Next, please. This is again the response which I have received from ChatGPT about introducing this HPC into the curriculum. Okay, so I'll share these PPTs later. So this is what it says, what contents are required at what stage and all those things. Next, please. Yeah. So that is all about the activities and the importance and the what you can expect from us as a nodal center. Okay.
Curriculum, we have to also introduce minor, major.
We have that, but as far as parallel is concerned, we haven't made anything as minor or major.
Honors we have to also.
Yeah, honors is also there.
And sir, your sponsorship, what exactly is sponsorship? Types of the project? Is it a parallel? It is like a core or it is application oriented?
Basically, it will be application oriented initially. Yeah.
Any problem they have?
Yes. Any problem which they want to solve using parallel computing. Initially, we are providing the supports to the faculty, and then because our bandwidths are limited, so now we have started conducting these kinds of programs across Maharashtra. Earlier, we used to conduct it only in Walchand College because we were not nodal center. We used to get help from C.I.T. for running these kinds of courses. But we thought that unless and until we spread this activity across Maharashtra at least, faculties will not be aware of all these things. Availability of resources is one of the important things. So we said that we will share all these resources. We will make it available. We will see that it will be a kind of, as I said, hand-holding process for the faculties. Because initially introducing any such new things into the curriculum is very difficult. Nobody will accept it. Nobody is ready nowadays to learn new things. That's the main problem. So we thought that let us give all the supports to the faculties, so that we can share the responsibility of handling a course, handling a practicals. And then once it is introduced to the students ultimately, once they get something, they will catch hold of this, and then they will develop the things on their own. So that is how we have started it. So we have conducted the programs in many regions now. We have conducted in Pune region, then Shivaji University of course is there, then we have conducted one program outside Maharashtra in Manipal University. We just wanted to ensure that it gets spread as much as possible. Because as I said, it is not a new technology. Again, remember, I have done a course almost 15 years back on this. And mostly the things are same, except CUDA, of course. CUDA has developed like anything. And that's why they are leaders, world leaders. CUDA, NVIDIA, everyone, and all the entire family. And it's not just, it is not like Intel. Intel has got different philosophy. What NVIDIA has done is they have provided full support to the academics. They have given the donation in terms of the hardwares. They have ensured that their contents, their curriculums, their programs are made available to the entire academic community. And then it was spread to the students. Of course, they have done it with the full integration to the US universities. That's why it is more developed there. Particularly in US and Europe, development is more. And that's why they came up with lots of hardware, lots of people are working on these things. And there are many Indians also who are working. So you'll find a lot of people working in this parallel computing. Okay. OpenACC chairman, I think, is some Indian lady. Okay. She has done graduation from here, then MS and PhD from US. There are many people. And one more thing I forgot to mention. There is one academic activity which is carried out by Professor Sushil Prasad. You can just note down the name. He has developed a website. Actually, they are getting grants from NSF, USA. Nowadays, it is very difficult to get a grant because of the new terms and new people. So what they did is their website is, you can just search for CDER, am I right? CDER, curriculum development something. And initially what they did is, again they spread this word about parallel computing, and they had organized some workshops in US, and all those workshops were sponsored fully for the Indian people. So I was one of the beneficiary of that. A lot of people have gone. We have presented this philosophy of putting it into a syllabus there in US in one of the conferences. And then based on all these inputs, they have developed their own syllabus, and that is available on CDER website. Okay. They are part of the people who organize that SC conference, supercomputing conference, which is one of the best conferences in the world. SC. So SC 25 is being organized, I don't know the month now. And the similar kind of conference is being organized, named as HIPC in India. It was held in IIS, not IISc, it was held in Bangalore last December 24. Every HIPC. H capital IPC. So this is again held, this will be held somewhere in November or December 25. And I think it is, I don't know where it is, Hyderabad maybe, if I'm not wrong. Okay. So you will get a chance, you can register for that course. They completely sponsor your stay and travel and everything. Okay. So look for these kinds of opportunities. You will get to know the people, you will get to know the hardware which is being used, you will get to know what are the current trends in this particular area. Okay. So Dr. Sushil Prasad, then we have one faculty member from IISc, then one madam from Manipal Institute of Technology. There are many people working in this domain. So these are some of the initiatives which are present. You can grab them, get hold to them, and then you can get the supports also directly from them. So as far as this high performance computing is concerned, we feel that this has to be made compulsory, introduced compulsory into the curriculum, so that students will also come to know about this, and they will develop on their own, and they will be able to use this technology to the maximum possible extent. Okay. Yes. Any other questions? Any other queries? Of course, you can write to us. I have given my email address. there is one more email address of the nodal center. You can contact any one of them to get more details. Okay. For that, first of all, you need to learn the basic things. So look for all these, I mean, go through some of the resources available. And then you can think of parallelizing anything, because there are many things which are not yet still parallelized. Like we used to have a mainframe earlier, and then we had developed the small computers, and then we had developed the appropriate software for those computers. So similarly, whatever standard algorithms which are being used, we can think of parallelizing them and then getting maximum out of it. The best applications are development of the AI models. AI models can be best developed with the help of these things, and then they can be optimized further. So optimization is the issue which could be used in using these parallel platforms. So you can address these issues in any domain, optimization. And in PAD, what we are doing is basically we are trying to optimize something. Of course, innovative things are there, but still in many of the cases we try to optimize with whatever we have. So there is huge scope. And as far as the applications, the consultancies are concerned, you can look for all the resources which are developed by NVIDIA. Many of the resources are being provided free of cost. And then using those resources, you can develop the things. Okay. Yes. What they have done is they have developed their own cloud also. So as far as conduction of, I think you have a course which is delivered tomorrow, right? On CUDA. Dr. Pikar, yeah, certification course. So for that, conducting that course, and they have made all this infrastructure available on cloud. So similarly, they will give you some cloud credentials, cloud credits for using these resources. Only thing is that you need to convince them that you are real users of it. But there are hundreds of platforms, hundreds of software stacks which are being provided. And for academic purpose, they give it very free. So you'll get very good support from them. And it's not only from NVIDIA. You can get support from, of course, I don't have very good experience with AMD, but Intel also supports that kind of activities. All right, any questions, any queries? So whenever you go back, maybe you can take some of your students into confidence and then start working on it, and then ensure that at least some of the contents are covered in the syllabus. If it is difficult to introduce these as subjects, at least introduce this as at least few of the practicals, so that they will get exposure, and then maybe subsequently you can put them as elective courses and then maybe core courses. But this route will take long time. So if you have power, if you are influential in your board of studies, then it's always better that take these courses as it is directly. And many of the IITs and IIScs, though I don't think that they are covering all these things into that depth. Of course, their students themselves are very bright, so they don't need all these things. And because our students are that way, we need to provide a lot of support to them. Of course, once some support is given to them, they can do wonders. So only thing is that we should give them some kind of exposure. And this parallel exposure is really essential and useful. And there is no cost associated, direct cost associated with all these things. All right, so thank you very much for patiently hearing. As I said, if you have anything to say, if you have anything to express or ask about, you can contact me on these addresses, email addresses. Thank you.
Okay. Thank you, Dr. D.B. Kulkarni, sir, I hope Dr. D.B. Kulkarni sir have answered most crucial question out of all, that is how to incorporate whatever we have learned today into our syllabus, and not only that, from where can we get further support, that is if we want to learn further, what should we look for, if we want to have further resources, whom we can contact and how we could create those resources, because when we talk about high performance computing is the biggest thing or biggest support that someone needs. Thank you, sir. Not only that, sir has also answered from his experience how should we begin if we want to do work in the research, or what would be the best way to deliver this particular part into chunks to our syllabus so that you don't change your syllabus drastically in the beginning. So thank you very much, sir, for your enlightening session. On behalf of all the faculties over here and organizing committee from the S.P.I.T, I would like to thank you, and we would like to present you a small token of appreciation. I call Dr. Pramod Bide sir to do the honors. Sir, please.
You done? Sir.
Tushar.
Thank you so much, sir.
Thank you, sir.
Before closing the session for free lunch, just I wanted to give you an idea about my journey in high performance. I wanted to. So, why I wanted to share, just because I wanted to motivate you guys, so that an ultimate aim of such type of FDPs under National Supercomputing Mission is to motivate students, motivate faculties across India, right? In order to create the awareness of parallel computing, awareness of parallel programmers, which are required in what we say digital India, startup India, and that's the main mission of National Supercomputing Mission of India. So I will just like to tell you, I participate in high performance computing. Of course, I have studied this subject, high performance computing, in my master's, right? But I was not good at OpenMP programming. I was not good at MPI programming. I was not good at CUDA programming, right? So when I participated in high performance computing workshop at C.DAC Pune, literally speaking, it was 14 days hands-on sessions, starting sharp at 9 a.m. till evening around 7 p.m. And we were staying at hotel, so we used to leave hotel around early morning 7 a.m. till 7 at C.DAC. We will reach around 8 p.m. in the hotel, and post 8 p.m. we have to complete the assignment. So just think of. And in the introductory session as well, right, I said that not only a young professor like me at the age of 35 years, there were few participants of 65 from Thapar University. They were literally coding on OpenMP, MPA and CUDA. And on the day one itself, they set a goal, right? Their C.DAC team, that you have to score 80%, then only you will be getting a master trainer certificate. Because of that, every participant, they were doing literally hands-on. The student, the way yesterday our MTech students and BTech students helped you guys, right, in order to do OpenMP and MPI programming in my lecture. Similarly, NSM team at C.DAC, they also have various volunteers. They help us, and every assignments, daily they were submitting one assignment, consisting of 5 to 6 complex questions, and that we have to solve. And because of this rigorous training only, I could able to adapt the new things and new technologies.
So what I wanted to tell you, and later on, as mentioned, there was one conference for master trainers at HPC Bangalore, HPC 2025. We participated there. So Dr. Sunil Prasad, Dr. Ashish Kuvelkar sir, and sir was busy, so sir was not able to come there. But Umesh Chauhan sir was there. So there is a team working on high performance computing in India. IEEE Computer Society TCPP is the main theme under IEEE Computer Society, also working on this particular high performance computing. And every year, high PC conferences are organized in India, right? Specifically in India. This year, last year it was in Bangalore. This year it is in Hyderabad, if I'm not wrong, Kulkarni sir. Yeah, it is in Hyderabad, right? So when I actually joined the C.I.T FDP, right, I gained a lot of knowledge on OpenMP and MPI, and because of the hands-on sessions, right? So see, 1 week hands-on sessions are really, and this that too we conducted in online and offline mode. But when you actually wanted to gain a more knowledge, you need to work on hands-on. The way you need to implement the codes, you need to understand the logic, you need to actually understand, right, where you need to apply hash pragma OMP parallel 4 or hash pragma OMP single, hash pragma barrier, right, hash pragma OMP single, atomic, masters, critical section when you need to apply, when you apply MPI gather, when you apply MPI send. Multiple activities we have seen in the inaugural session and in yesterday's lecture also. So if you gain that type of knowledge, then it will be easier to understand any other code, right? So what I will insist you to, don't stop it here, right? Try to gain more knowledge, work on the hands-on sessions, and what I help you is I will again give thanks to our head of the department, because he has given, since I completed master trainers, he has assigned me 2 subjects on HPC, BTech and MTech. And again, I dwell into it in depth to teach the students, and teaching at S.P.I.T to UG students, new subjects, I need to, it's very difficult because students, what type of questions students will ask, we'll never know. So that's the reason again I dwell into more in depth of OpenMP and MPI programming, and that's why I could able to speak about OpenMP, MPI, and I could able to deliver some sessions in front of teachers like you. So what I will suggest and recommend, don't stop it here, add hands-on knowledge, right? And once the hands-on knowledge is completed, do participate in NSM activities. Henceforth, right, you people will be, we have emails with you, and whatever teachers, right, completes the course, completes the FDP, right, all activities under NSM, all activities under Nodal Center, all activities under high PC domain or TCPP domain, right, we will be mailing you guys, every time we'll be receiving. So if you are interested, please register and please do participate in it, okay? So that's what from my side. Thank you. Lunch is ready. We can proceed for lunch. Yeah, there is a session. R.K. Joshi sir's session. Post lunch. Yeah. Sir is on the way.